Hello students, this is your friend Sumit and today we are going to discuss topic 16 of the series, that is modern physics. Modern physics is a topic which is having very high weightage, and this particular topic is independent of all the topics whatever you have understood so far from entire physics. So if you don't understand anything, it's okay, you can understand modern physics. Modern physics do not have any prerequisite. It is completely independent topic and one of the simplest topic. If you ask me, sir, tell me one topic which is very easy to understand and very scoring, I'll say that is modern physics. Very difficult to make mistakes in modern physics because there is very limited scope. Modern physics include 3 chapters. The first one is dual nature of radiation matter, second is atom, the third one is nuclei. From nuclei, the radioactivity portion is not in main, so we are not going to discuss the radioactivity portion. Other things we are going to discuss in detail from very basics. Okay, even if you don't understand anything from modern physics till now, you will be perfect after watching this one shot, and you will be able to solve any questions from mains. Okay, so let us start the discussion, and after watching this video completely, don't forget to get the class notes and the DPPs for your practice. Class notes will help you to revise entire thing very quickly what we are going to discuss, and from DPP you can do a good amount of practice. So that you will get from the link that is given in the description. Click on the link, you will go to the PW app, there you will join the free batch. From that free batch you will be able to access both the things. Okay, and yes, again I'm highlighting practice is very important. So let us begin our discussion. We are going to discuss the 3 chapters. First is the dual nature of radiation and matter, second is the atoms, and the third one is nuclei. From nuclei, in mains, as you know, radioactivity portion is not there, so we'll not be discussing that portion. Okay, and from all other things are there. Okay, from dual nature, if I talk about the most important means the topics of very high weightage is specifically the photoelectric effect. Okay, almost in every paper we see, almost in every paper, like we have questions from photoelectric effect, and also the dual nature, finding the de Broglie wavelength, that is also important. From atoms, Bohr's model. Okay, many of the questions are asked from Bohr's model. Find the radius of this, find the ratio of radius of these two orbits, or find the energy of excitation, or how much energy will be released, how much will be the wavelength of the photon. Okay, or how much of the photon, how much is the wavelength of the photon needed for this excitation. So these kind of things are very much asked. From nuclei, if I talk about finding the mass defect, okay, and then you can say finding how much is the you can say binding energy of a nucleus, or how much will be the Q value, and the third thing is the size of the nucleus. Size of the nucleus thing is also very much asked sometimes, like what will be the ratio of the density of the 2 nuclei that is asked, and yeah, we have seen such type of questions. Anyways, we will take all those varieties. So first of all, let us talk about electron emission. As we know, metals, they have conduction electrons, they flow freely throughout the metals. Okay, now these electrons are available on the surface also. Now, is it possible to extract those electrons, or is it possible for the surface to emit those electrons? Now, certainly that is possible, but it will not happen on its own, because these electrons are certainly bound to the metal. Okay, so now we need to give a certain amount of energy to these electrons to free these electrons. Okay, like take an example, like satellite is there, satellite is bound to the planet. We need to give certain amount of energy to the satellite so that the satellite will be free and will escape. So in the same way, just an analogy. Okay, so these electrons are bound to this metal. If you want to free these electrons from the surface, you need to give certain minimum energy, and that minimum energy we call as the work function. Okay, so work function is defined as the minimum energy required by an electron to escape from the metal surface. Now, you can give greater energy. Okay, so minimum energy is this much. If you give some extra energy, what will happen? The electron will have that extra energy as its kinetic energy. Okay, so minimum energy is there. If you give any energy lesser than that, the electron will not be able to you can say leave the surface of the metal. Now, what all different ways are there to supply this energy? There can be different ways, yes. So These primarily these three ways are there. Okay, first is thermionic emission. Here you are giving heat energy to the metal. Okay, so heat energy you are giving, supplying, so electrons are gaining energy. Eventually the electrons will have sufficient energy to leave the surface of the metal. Second is the field emission. Field emission means you apply very high electric field. Okay, you apply very high electric field such that the electrons are pulled out of the surface of the metal. And the third is the photoelectric emission. Here you the photons are there. Okay, so you put photons on the surface of the metal, so these photons will come, the electrons will gain energy from these photons and they will leave the surface of the metal. Okay, so photons are having some energy. Okay, the electron will absorb the photons, those energy electrons will get some amount of energy, the electron will give to the metal, because that is the text means the work function of the metal. Okay, so that work function they need to pay to the metal, and the extra energy the electron will have as the kinetic energy, and then the electron will leave. Like, so basically we will be talking about this thing, we will not be talking about the first two. Third thing, and yes, this is the most important thing of this particular chapter. If you are not doing anything from this particular chapter, dual nature of radiation matter, don't skip this. Now, let us talk about what photoelectric effect is actually. Now, it was observed by Helmholtz and Leonard that when the rays of a light fell on the emitter plate, okay, so this is my emitter plate, this, the rays of the light fell on the emitter plate. Okay, the electrons were not emitted unlit. When the rays of the light fell on the emitter plate, the electrons were not emitted until the light frequency was smaller than a certain amount. So if you increase the frequency, then the electrons are emitted. Okay, this was one observation. Okay, so if you increase the frequency of the light, then means, as I was saying, they need sufficient energy. If the frequency is low, sufficient energy is not available for the electrons, they are not able to leave the surface. Now, if you increase the frequency of the light, what happens? They have the sufficient energy. Now the electrons will leave the surface. Okay, like this. They will travel like towards the collector plate. Okay, so this collector plate will capture all these electrons and will have a current here, and that current will be detected by this ammeter. Now, this current certainly will be very small, therefore we need an ammeter which can measure current of the order of microampere. Okay, so sometimes we write this as my microammeter. Okay, means it is having the range in microampere. Okay, so light is coming, falling on the surface, electrons gain energy, some part of the energy they will give as the work function, some part they will have as the kinetic energy, and they will leave the surface. Okay, now this collector plate will be there, the electrons will be you can say collected by this collector plate, and this is how the current will be detected. Okay, so this observation was done. Now we are applying here potential also. Here we can vary the intensity of the light, we can vary the frequency of the light, we can vary this applied potential also. We can make this as positive or this as negative. Okay, these type of variations we can make, and then we will see how the current is varying, how the current is affected by changing the intensity, how the current is affected by changing the frequency. Okay, how that current will be affected by changing the potential. So these kind of observations were also made. Let us discuss those observations. So first, here effect of intensity of light on photo current. Here we are increasing the intensity of the light, and here we are measuring the photocurrent. Now photocurrent means what? The current here you will see. Okay, so this is my photoelectric current. Getting it? So here the current that will flow in this circuit, that is my photoelectric current. So that current I am measuring. Now in this, what is kept constant? Frequency is kept constant. My applied potential is kept constant. Okay. Now I am varying only intensity. As I am varying intensity, you see the photocurrent is varying linearly. Means if you double the intensity, the photocurrent is also getting doubled. Yeah, we'll talk again about this observation and we'll draw a conclusion at the end. Okay, so this you should keep in mind, that if the intensity increases, then what happens? The photocurrent increases linearly. Means if intensity becomes double, this also gets doubled. It's directly proportional, not only linear. Next is effect of potential on photoelectric current. Here we are keeping my frequency and intensity, we are keeping this as constant. Previous observation I can say, we got that my current, my I, small I can represent, okay. So this comes out to be proportional to the capital I, this is my intensity. And this is my photoelectric current. Now next, here I am keeping the frequency and the intensity as constant, and then I am varying the potential, and then I am seeing how the intensity is changing. Okay. Now if you see, let us take for the positive side, when the potential is positive. If I apply positive potential means my this side is positive, okay, this side is positive. So these electrons are which charge? Negative charge, isn't it? Yeah, they will be attracted towards the positive charge, yes, and they will go like this. But if you see one thing, here a little bit increase is there, but if you keep on increasing the potential, my current is not increasing, that remains constant. Okay, that saturates. It means the number of electrons that are emitted is independent of the potential. Yes, the number of electrons that will be captured here, okay, the number of electrons that will be captured by this collector plate will increase a bit when you increase the potential initially. Why so? Because now positive charges, all the electrons are able to reach there. Now once all the electrons are able to reach there, you increase the potential, the count will not increase, because that count is depending upon the intensity, not on the applied potential. Yes. So it is increasing a bit, but then it saturates. Okay. So here in this range I can say it saturates. Increases a bit, but finally that's saturated. Now we are applying the negative potential. Now if you apply negative potential means you made this plate as negative. Now negative will repel. It means this here the field will be actually slowing the electrons. As electrons are moving, they will be getting slower and slower. Okay. Now you are applying certain negative potential, but electrons are having some kinetic energy. That is like they are able to overcome that, you can say, electric field, and they are able to reach the collector plate. But if you too much increase, then what will happen? No electron will be able to reach there. The electrons will not be able to reach there. Now here you see I'm putting the negative potential. Okay. So when the potential is a bit negative, certainly here my current is lesser. But if the potential is sufficiently negative, this photocurrent becomes zero. And this particular potential we call as the stopping potential. Stopping potential means what? You stopped the electrons. Okay, the electrons are not able to reach. You applied sufficient negative potential such that no electron is able to reach. The photocurrent becomes zero, and this potential we call as the stopping potential, or sometimes we call this as cutoff potential. Stopping potential, or sometimes that is termed as the cutoff potential. If you applied that potential, then what will happen? No electron is able to reach. The photocurrent will become zero here. Now if I increase, if let us take one intensity I was taking, now let us take, if I draw the same curve for another intensity, what will happen? If the intensity I2 is higher, this curve will be like this for higher intensity. If you increase the intensity further, this curve will be like this. What does it mean? My stopping potential is independent of the applied frequency. Sorry, stopping potential is independent of the intensity. All the three intensities are having same stopping potential. Yeah. So my stopping potential is independent of intensity. My photocurrent, count of the electrons was proportional to the intensity, but the energy of those electrons is independent of the intensity. On which they depend? They depend on frequency. We will talk about that. Okay. So this is how this curve will come. Next now. So here, effect of frequency of incident radiation on stopping potential. Now if we change the frequency of the light, then how the things will change? Okay, here my you can say this is my photoelectric current, okay, and this is my potential, applied potential, okay, and these three different frequencies we are taking. On one of the curve, if you take, the frequency is constant, okay, and my intensity is constant here on one of the curve. Okay, so I can say frequency and my intensity here I am taking as constant. Okay, yeah, like that for one of the curve. Here the frequency is different, here the frequency is different. Now from this I can say that if the intensity is same, this final photoelectric current that we are getting, that will remain the same. It means what? If your frequency yeah, one point is there, we will talk about that in a while. Okay, so this my photoelectric current here is same, means this saturated value of the photoelectric current is same for all the three frequencies. It means it is coming independent of the frequency. How much photoelectric current will be there, means the final saturated value is coming out to be independent of the frequency. That depends on the intensity, not on the frequency. Okay, so I can say my photoelectric current is independent of the frequency. Independent of the frequency. Yeah, here I should write, okay, considering the frequencies above a certain value, okay, frequency that is above a certain limit. This we will talk about. This above a certain limit, this we call as the threshold frequency. Okay. Now you see here this is same for all the three frequencies, but the stopping potentials are different. Stopping potentials are different. It means the kinetic energy of the electrons, are different. Means stopping potential that you are applying, you are stopping the electrons. Greater the kinetic energy, greater potential you have to apply to stop them, isn't it? Yeah. So when this frequency is increasing, you have to apply greater potential, means in magnitude, okay, to stop them. It means what? The kinetic energy actually depends on the frequency. The kinetic energy of the electrons depend on the frequency, not on the intensity. Okay, let us write that also. So the kinetic energy of electrons depend on frequency, okay, not on the intensity. Greater the frequency, greater will be kinetic energy. If kinetic energy will be greater, you have to apply a higher potential to stop them. Therefore, the stopping potential is increasing. Therefore, I can say thus my mu3 is greater than mu2, which is greater than mu1. Okay, so here this mu3 is greater than mu2, which is greater than mu1. Frequency is increasing, kinetic energy increasing, the stopping potential is increasing. I have to apply a greater force to stop them. Greater force means a higher field. Higher field means the potential is greater in magnitude. Okay, so don't see, sir, that is a negative now. Don't get confused. I am talking about the magnitude. Okay, next is here we are seeing how the stopping potential and varies with the frequency. Okay, so we see here this curve is a straight line. Okay, why this curve is a straight line, we'll talk in a while. And here I can say if the frequency is lesser than this, it means we need not apply any potential to stop. It means the photocurrent is zero, no electron is coming out. It means electrons will only come out when the frequency is greater than a certain limit, and this limit we call as the threshold frequency. So this is my threshold frequency. Okay, so this is my threshold. Threshold frequency. Electrons will only be ejected when the frequency of the incoming the photons, or I should say the incoming radiation, is greater than a certain limit, and that limit is my threshold frequency. Okay, so electrons, let us write that, will only be ejected if the frequency of the incoming radiation is higher than a certain limit okay, certain limit called the threshold frequency or the cutoff frequency. The corresponding wavelength also sometimes we call as the threshold wavelength. Sometimes instead of threshold frequency they ask for threshold wavelength. This is the same thing. Okay, the corresponding wavelength we call as the threshold wavelength. Now minimum frequency is needed. It means some minimum kinetic energy, as I mentioned here, that some minimum energy you have to give to the electrons such that they will leave, and that minimum energy will be provided by the minimum frequency, that is my threshold frequency. If any light of frequency less than that, no you can say photocurrent will be there, photocurrent will be zero, as it was observed initially. Okay, here what was observed? When the rays of the light fell on the emitter plate, electrons were not emitted until the light frequency was smaller than a certain amount. Okay, if I should say the electrons were not emitted until the light's frequency was smaller than a certain amount. I think greater than a certain amount. Electrons were not emitted until, if it is greater then it is emitted. Okay, what frequency means, if the frequency is lesser than a certain limit, the electrons were not emitted. I think you got this point. Is the statement correct or not? Like, electrons were not emitted until the light frequency was smaller than a certain amount. Yeah, it is not emitted if it is less than a certain amount. If it is more than that, that will be emitted. Okay, so that amount that I am talking about is my threshold frequency. Okay, so all these observations were you can say made experimentally, and from these observations certain conclusions were drawn. So let us quickly revise those conclusions. We have already discussed these conclusions. So quickly let us see. First is the photoelectric current is directly proportional to the intensity of the incident radiation. Yes, above the threshold frequency. Yeah, this point is important. You know, the frequency should be above the threshold frequency. Otherwise, no point of discussion, means otherwise no photocurrent is there. Now, for a given photosensitive material and frequency of incident radiation. Okay. Second is saturation current is found to be proportional to the intensity of the incident radiation, whereas the stopping potential is independent of the intensity. Stopping potential is independent of the intensity. It depends on what? Frequency. Okay, kinetic energy has a relation with frequency, stopping potential has a relation with the kinetic energy. Okay, so these three are related. Photocurrent is related with the intensity. Next, there exists a certain minimum cutoff frequency. Okay, yeah, minimum cutoff frequency, which we call as the threshold frequency of the incident radiation, below which no emission take place for a photosensitive material. Okay, irrespective of the intensity of the incident, doesn't matter how high the intensity is. If the frequency is below threshold frequency, no emission will be there. The maximum kinetic energy or equivalent stopping potential above the threshold frequency of the emitter photoelectrons increases linearly with the frequency. Yeah, that relation is linear. Okay, how that is linear, we will talk in a while. The photoelectric emission is an instantaneous process. Now, this is the point that we have not discussed till now. Now, this photoelectric emission process is instantaneous process. Like the light falls instantaneously, the electrons gain the energy, they leave the surface. Okay, so the time lag is very small between the incidence of radiation and emission of photoelectrons. How small? Nanoseconds. Okay, it is of nanosecond. Okay, even when the incident radiation is extremely dim, means even if the intensity is very small, if the sufficient frequency is there, frequency is above threshold, emission will take place, and that emission is instantaneous. Why these conclusions are made? These conclusions are made such that you understand that in this particular phenomena, a particular you can say nature of the light dominates, and that nature is the particle nature. Particle nature dominates. Now, according to wave theory of light, if we try to draw the conclusions, they contradict what we have got the experimental observations from this photoelectric effect. Okay, they contradict with that. Let us discuss this. The first point, the maximum kinetic energy of the electron according to wave theory should depend on the intensity, not on the frequency. Why so? If you consider light as a wave, then the energy or the intensity, if I talk about, of that depends on what? Amplitude of electric field, magnetic field, isn't it? Yeah, that is the EM wave. How we write the intensity? Half epsilon naught E square into C. This is how we write. Okay, so that intensity basically depend upon the amplitude of the electric and magnetic field. Okay, that is independent of the frequency. So, if that depends on that, it means the kinetic energy of the electron should depend upon the, should be independent of the frequency, they should depend upon the intensity, but that is not happening. That is not happening. Okay, my maximum kinetic energy depend upon the frequency that we have observed. Okay, yeah. So, this first is actually, you can say, incorrect statement if we observe according to wave theory. Okay, according to wave theory, the maximum kinetic energy should depend upon the intensity, but that is not coming. It means this is incorrect. It means wave theory is not able to explain this particular point. Next thing, the threshold frequency should not exist. Why? Now, energy depend upon what? Intensity. If intensity is above a certain limit, then the electron should be able to, you can say, leave the surface. Doesn't matter what is the frequency. It means there is no point of threshold frequency according to the wave theory of light. but experimentally it is observed that we need light of certain, above the certain limit that we call as the threshold frequency. So this is also incorrect. Okay, it is existing. It means wave theory of light is not able to explain this point also. Next is, it can take hours or few more for a single electron to pick up sufficient energy. Now what happens? Let us take a particular intensity is falling on the surface. Now so many electrons are there. Okay, so if you talk about this is I am talking about this as a wave. Okay, now so many electrons are there. If you talk about how much energy per electron will get, that will be very less. Okay, then less energy, it means it will take more time to it will absorb energy for a greater amount of time. It's a wave. Okay, that wave is coming, it will absorb that wave for a longer duration to leave the surface, because it is getting very small fraction of that, okay, particular electron. So and if we actually try to calculate how much time that should be, that comes in hours actually, but photoelectric effect happens in instantaneously, means the order is of nanosecond. It means this is also incorrect. This is also incorrect. So according to wave theory of nature, we are not actually able to explain the photoelectric effect. It means in photoelectric effect, the particle nature of the light dominates. Light has two nature, particle nature is there, wave nature is there. Now wave nature of the light is shown by in YDSC, yes, my interference is happening, diffraction is happening, there my wave nature of light is there. I cannot explain those phenomena with the particle nature, okay. In diffraction or interference, I cannot explain those phenomena with the particle nature of light. I can only explain those with wave nature of light, how the phase difference is coming, okay, how much part difference is there, how much is the phase difference is there, how they are interfering with each other constructively or destructively. Accordingly I show you, this is how the intensity is varying, here we are getting maxima, here we are getting minima. That cannot be explained by the particle nature. That shows the wave nature of light. Now the photoelectric effect actually shows the particle nature. If you try to explain this by wave nature of light, you get the wrong conclusions, and these three are wrong conclusions. Okay. So here I can say the particle nature of the light dominates. Okay. Particle nature of the light dominates. Now let us discuss the particle nature of light. Now here we are considering that my light that is coming, this is made up of small energy packets. Light is energy, okay. That radiation, that light is made up of small energy packets, and those energy packets we call as the photons, okay, or the quanta or quantum of energy, the smallest unit, okay, there, okay, those small energy packets. So light is made up of, or I should say, let me write in simple words only, made of small energy packets okay, and these energy packets we call as the quanta or quantum or photons. Okay, same thing as the photons. So that there comes the quantum mechanics, where we consider the light made up of small particles, and these particles have their momentum, have their energy, they have some speed. Okay, so now we analyze these like small particles, just like particles. Now wave is not there, just consider them like a particles, and then you analyze everything. Okay, so now these particles will have some energy. How we denote that energy? We write that energy E, let me write as energy of each packet, or I should say, I have already termed that as photon. So if I write energy of photon, okay, photon, it should be photon. Yeah, energy of photon, let us denote that with E, that is equals to h, the Planck's constant. into the frequency. Frequency sometimes we denote with f, sometimes we denote with mu. Let us write as mu. Here h is my Planck's constant. Okay, and mu, Planck's constant is 6.6 into 10 to the power minus 34. And if you talk about the unit, so this is joule second. Energy is having the unit of joule. Okay, this is frequency, so that is 1 by time. If time comes here, that becomes second. Okay, the unit is second, so joule second, like that. So Planck's constant and mu is my frequency. So energy of each packet depends upon the frequency. Basically, Planck's constant is my constant. Planck's constant is constant, that is not going to change. Okay, so basically the energy of a photon or energy of this my smallest particle of the light, that depends on the frequency, and that frequency is mu. Okay, so the energy becomes h into mu. I can also write this in terms of speed and wavelength. Speed, you can say, is my c, that is speed of the light. Frequency, mu, I can denote as I can relate with the speed as c divided by lambda. Frequency into the wavelength is my speed of light. Remember this, frequency into the wavelength, this is the speed of the light. Okay, in free space I'm talking about. So I can write mu as c by lambda. So I can write this as h c by lambda also. Let us highlight it. Yeah. Okay. Now let us take, there is an energy beam. There is a beam. Okay, and there you are mentioned that this beam, from this beam, n number of photons per second are ejected. Okay, n number of photons. So how much is the, you can say, power or like that. So energy of one photon, multiply that with n, that will become your energy that will be emitted per second. So if there are n number of photons, so if n if there are n number of photons, let me write like this, if there are n photons, my energy will become n times of the energy of the each photon, like this. Okay, now these particles, they have their momentum also. Their momentum, it means there is some relativistic mass also that is related with these. Yes, so I can write the momentum as energy, I can write as E is equals to mc square. Okay, so if I write energy E as my m into c square, and this also I can write as hc by lambda, Okay, so from there I can say m into c. This photon is speed of light only. Okay, so m into c, that becomes my momentum, and that is coming out to be h by lambda. Okay, so from there I got the momentum of photon as my h by lambda. Momentum of photon is h by lambda if lambda is my wavelength of that photon. So this is how I can write the momentum. Certainly if momentum is there, it means if they strike a surface, there will be certain pressure also. Okay, corresponding force will come, corresponding pressure will be there on the surface. Now, and that pressure we call as the radiation pressure. Now radiation pressure I am not going to talk here, because I have already covered that in EM waves. So in the portion, in the one shot of AC and EM waves, there I took the radiation pressure. So I am not discussing radiation pressure here. I will not be taking questions of radiation pressure also, because I have already considered the question there. So let me write here a note for you all. We'll be revising it. Okay, let me write a note for you. radiation pressure is already covered in EM waves one shot. Okay. So that is already uploaded. So in EM waves one shot, we have already covered the radiation pressure. So we are not going to discuss radiation pressure here. So don't think, why sir skipped, why sir is not taking questions, although those questions are asked in mains. Now let us do some of the questions here. Monochromatic light of frequency this is produced by a laser. The power emitted is this much. How many photons per second on an average are emitted by the source? I know the energy of one photon. Let us take there are n photons. Total energy per second will become n into the energy of one photon, and that is equal to my power. Okay. So let us write. So my power will be the number of photons per second into the energy of each photon, that is h into mu. So from there I can find what is n. N will become my power divided by h into mu. Now what is power here? That is 2 into 10 to the power minus 3. So 2 into 10 to the power minus 3 divided by, what is h? H is 6.63. Okay, 6.63 into 10 to the power minus 3, 34. Sometimes, like generally we consider till only one decimal place. Okay, so don't think like sir mentioned here value of h as 6.6 and it is 6.63. Generally we consider till one decimal place. If you want to consider till two decimal places, you can consider 6.63. Because in modern physics, if you see, there are so much calculations in many of the questions. So in generally talking about, in many places you will see that the options are not very close. It will not be like 6.63 and the second option is 6.62. Options will not be there like that. Okay, so don't take need not consider till that third decimal place or second decimal place like that. Anyways, 6.63 into 10 to the power minus 34 into the frequency. How much is the frequency? Frequency is 6 into 10 to the power 14. So 6 into 10 to the power 14. How much it is now? 10 to the power will be, this 14 is there, minus 20, so 10 to the power 17 will become there in the numerator. Okay, yeah, this is 34. Okay, 34 with 14 minus 20 will go in the numerator, minus 3 is there, so plus 17 will become. And let us write it like this: 200 into 10 to the power 15 divided by 17 was there, I took two zeros here, 6.63 into 6. You can help me with the calculations if you can. Let me do. This is a recorded class. This is a recorded class, so therefore you cannot help me in the calculations. So what it is, this is 200 divided by 6 divided by 6.63. So this comes out to be 5.027 into 10 to the power 15. 5.027 into 10 to the power 15. So that is option C. Okay, now here when we write this hc by lambda, when we write the energy, we are taking everything in SI unit. H we are taking in SI, C is speed of light, that will take as 3 into 10 to the power 8, you all know, therefore I am not writing again here. Lambda is the wavelength, and then that we will write in SI, although wavelength are most of the times given in angstrom or you can say nanometer like that. Okay, so we will convert that to meters and we will put here. So the unit will be you can say energy, that is joules. But sometimes or many times it is helpful that let us take all the calculations are given in electron volt, that you will see when we will come to the Einstein photoelectric effect equation. Okay, so there you will see the calculations are actually in electron volt. There we need to convert the joules into electron volt. So if you have to do that conversion, so remember it, where should I write? Here I should write. Okay, so 1 electron volt is basically equal to 1.6 into 10 to the power minus 19 joules. Keep this in mind. Keep this in mind. Okay, and if I try to write this Hc in electron volt angstrom, so this nearly comes out to be 12,400. Okay, this is in my electron volt angstrom and divided by my lambda. So now you put the value of lambda in angstrom, you will get your corresponding energy in electron volt. Many times it helps a lot, okay, to speed up the calculations. You know a photon of particular wavelength, you want to write how much is the energy in electron volt, quickly you can put the lambda here and find an electron volt. Now this 12,400 is, you can say, approximation is there. Okay, so it is not, to up to such decimal places is accurate. No, so sometimes in the question only they mentioned, take this Hc as 12,450 or sometimes 500 electron volt angstrom. So like that, if that is given in the questions, you can use that. So you keep this in mind, it helps in calculation. I can do, let me edit this, let me extend it here till here. Okay, yeah, now it is fine. To help you in calculations, I mentioned that. Next question is there. Let us read. Given below are two statements. First is, two photons having equal linear momenta have equal wavelengths. So how we write the linear momentum? Linear momentum we denote with P. How we write that? H by lambda. This is my momentum. Okay, that momentum only depend upon the wavelength. If the wavelength is same, it means they will have the equal linear momentum. Yes, this is correct. Next statement, if wavelength of photon is decreased, then momentum and energy of the photon also decreases. How energy is related? This is my momentum. Okay, how energy is related? With the wavelength Hc by lambda. So here it is mentioned, if the wavelength of the photon is decreased, let us take your decreased lambda, then momentum and energy of the photon will also decrease. No, if you decrease lambda, energy increases and momentum also increases. So the second statement is incorrect. So I can say statement 1 is true and statement 2 is false, that is option D. Higher the frequency, higher the energy of the photon. Keep this thing in mind. As I had mentioned previously, that as the frequency is increasing, the energy of the photon is increasing. Energy is increasing, momentum will also increase. So it means that relation will be inversely proportional to the wavelength. Frequency into wavelength is equal to speed of light. Speed of light. Okay, speed of light in vacuum, that is constant 3 into 10 to the power 8. If you increase frequency, wavelength will decrease. Okay, see this relation again. Speed of light is equal to mu into lambda. If you increase frequency, c will remain same, lambda will go down. If you decrease frequency, lambda will go up. Frequency, if it is increased, energy will increase. Okay, E is equals to h mu. Frequency is increased, my energy will increase, my momentum will increase, if wavelength is increased, energy is decreased, wavelength is increased, energy is decreased, and the momentum is also decreased. I mean, I am repeating these things. Sometimes you may say, why is teacher is saying again and again. I am repeating so that you are very clear with these concepts. Okay. Now coming to Einstein photoelectric equation. Okay, It's not a difficult equation, very straightforward equation, just based upon conservation of energy. So conserve the energy. I'll say my photon that is falling is having certain energy. Okay, how much certain energy? That is my h into mu. This is the energy of the photon. This photon is absorbed by the electron. Now electron got that energy. Electron will leave the surface, but before that the electron has to pay the tax. Okay, and what is that tax? Okay, that is the work function. So like we get salary. Salary comes, okay, but it's not that you are having let us take certain amount of salary and you will get all that amount. No, government will deduct something. Okay, so this is the tax you have to pay, and the rest of that you will get. So same thing, electron gets some energy, the photon comes, electron absorbs that photon. Now this electron has to pay the work function. So certain amount will go to the work function and rest will remain as the kinetic energy of the electron. Okay, rest will remain as the kinetic energy of the electron. So I can say that my kinetic energy of the electron will be equal to the energy of the photon minus the work function. Here we are not considering any other losses, so sometimes we write this as the maximum kinetic energy of the electron. Okay, we are not considering any other thing. Total energy that is coming minus the work function, that is my kinetic energy of the electron. We write this as the maximum kinetic energy of the electron. So this becomes my photoelectric equation, Einstein's photoelectric equation. Very easy to remember. Just conserve the energy. Now, if this energy, this equation is all the terms are given in SI units, take everything in SI unit. Sometimes or most of the times actually the values here will be given in electron volt, because these are very small. Okay, so 2 electron volt, 3 electron volt, these type of things are there. If you mention them in joules, it will be like 10 to the power minus or like that. So to avoid all those complications, here the things are mentioned in the electron volt. So generally we talk about how much will be the kinetic energy of the electron, and the options will be in electron volt. So I'll tell you how to deal in electron volt here. Now this kinetic energy the electron is having when the electron left the collector plate, not collector plate, emitter plate. When the electron left the emitter plate, here, this electron is having that kinetic energy. Okay, now if you have to stop that electron, it means you have to do same amount of work in the opposite sense to stop. Let us say some ball is coming towards me, it is having some kinetic energy k. I have to stop that. How much work I need to do? K. Why so? Means that will be negative in nature certainly, but I have to make that kinetic energy 0. So I have to apply the same amount of energy, okay, to stop that. So same thing. Here you want to stop that. Let us take the stopping potential as V. So stopping potential is V, considering this as negative, okay, this as positive. Stopping potential is V. Now the work, the stopping potential that will do, that my E into V, charge into the potential, that will be equal to the kinetic energy if you have to stop that electron. So this kinetic energy, this maximum kinetic energy of the electron, I'll write this as E into Vs. This will be the work done by the stopping potential to stop it, and that has to be equal to the kinetic energy, then only your electron will be stopped. So this, let me write here, is my stopping potential. This is the stopping potential needed to apply to stop that electron. So this equation, if I have to write for stopping potential and the frequency, so how I can write this equation? Let us write it here again. So I can write that my E into V stopping comes out to be H into mu minus phi naught. This E I can take to the denominator there. So V stopping comes out to be H by E into the frequency minus phi naught by E. Minus phi naught by E. So this relation becomes between the stopping potential, the work function, the applied frequency. I was saying previously, I discussed this graph and I told that this is a straight line. Why it comes? We'll talk in a while. So this is where we are talking this. Okay. So here this is my stopping potential. Okay. This is my frequency mu. It is having a slope of h by e. This theta. So if I say here this my tan theta is h by e. And the intercept will be there. If I extend this on the other side, if I extend this on the other side, this negative intercept is my phi naught by E. This is my negative intercept. So this much is my phi naught by E. Okay. Now threshold frequency was the frequency at which the electron is just emitted. Just emitted means with zero kinetic energy. If the kinetic energy is zero means the stopping potential is also zero. So if you put the stopping potential here 0 or the kinetic energy here 0, you can relate with your threshold frequency and the work function. Okay, getting the point? So I can say that my threshold frequency mu naught comes out to be phi naught by h. This is how we relate the threshold frequency and my work function. So this is my threshold frequency. And phi naught is my work function. So threshold frequency is depending upon the work function. It's not depending upon the intensity, it's not depending upon any of the thing, it depends upon the work function, because this is relating the minimum energy, with the minimum energy that you need to provide to the electron to free it. Free it means it is coming out with the zero kinetic energy. If the frequency is less than this, it means this will be negative. This term will come out to be negative. Kinetic energy cannot be negative. It means what? The electrons will not be ejected from the surface of the metal. Make this a point. I am repeating the same point. If the frequency is less than the threshold frequency, the kinetic energy is coming out to be negative. Negative means kinetic energy can never be negative. It means here the electrons will not be ejected. Write this point down in your notebook again. Electrons will not be ejected for the condition when the frequency applied is less than the threshold frequency. Okay, now I mentioned any of the equation, either this equation or this equation or this equation, whichever equation you are using. If you are using in SI units, means you are dealing with joules, so keep everything in SI unit. If you are dealing in electron volt, keep everything in electron volt here. Don't mix the things up. If you mix, you will get confused. Now, as I was saying, generally we will be dealing with electron volt. Now, I'll show you how we deal with electron volt. You will learn. I'm having many questions on photoelectric effect, because actually these are the things which are very much asked, very much asked. Means if something is coming, very high probability from this chapter that if something is coming, it will be coming from photoelectric effect. If that is not, then from de Broglie wavelength. Hardly there is anything else. A light source of wavelength 2 illuminates a metal surface. A light source of wavelength 2. I think something is missing here, isn't it? It should not be wavelength 2, it should be some unit should be there. whether it is nanometer or something. Let me check. Let me see if I can check right now. This is page number 16. I am having light source of wavelength lambda. Yeah, that should be lambda, and then we are having lambda by 2. So this is incorrect here. This is lambda. So light source of wavelength lambda illuminates a metal surface and electrons are ejected with maximum kinetic energy 2 electron volt. I can relate the kinetic energy K as my, this is in wavelength is given. Okay, so let us relate with the wavelength then, hc by lambda minus phi naught. Either I can write hc by lambda or h mu, same thing, don't get confused. Okay, so this is h mu only. If lambda is given, this write this as hc by lambda, same thing. So hc by lambda minus phi naught. This is how. If the same surface is illuminated by light of source wavelength, that is lambda by 2, then the maximum kinetic energy of the ejected electrons will be, work function is given in electron volt. Let us put everything in electron volt. Now I am considering everything is in electron volt. Okay, so case 1, wavelength is lambda and the kinetic energy is 2 electron volt, the maximum kinetic energy. So I will say my 2 electron volt is equal to hc by lambda minus phi naught. Second condition, lambda becomes lambda by 2, the maximum kinetic energy will be, and phi naught is given as 1 electron volt. This is 1 electron volt, so let us write this as 1 electron volt. This is my first equation. I can take this 1 electron volt here. So I got 3 electron volt as hc by lambda. So this is my first equation. Next condition, lambda becomes lambda by 2. If lambda becomes lambda by 2, what will be the kinetic energy? So I can say again, kinetic energy is equals to hc divided by lambda by 2. Okay, lambda becomes lambda by 2 minus the work function, that is 1 electron volt. hc by lambda is 3 electron volt. 3 into 2, this becomes 6. So 6 electron volt minus 1 electron volt. This is K dash, the new kinetic energy. So K dash becomes 5 electron volt. 5 electron volt it is. That is option C. This was easy question. Next question. A photoelectric effect. In photoelectric effect, an EM wave is incident on a metal surface and electrons are ejected from the surface. Okay, if the work function of the metal is this is an electron volt only, and stopping potential is 2 volt. This is my stopping potential. What is the wavelength of the EM wave? Hc, here you see this, Hc is given like this. This here they put nanometer instead of angstrom. If you take angstrom there, it will become 12420. Generally we take 12,400. Here it is mentioned 12,420. Sometimes you may find like 12,500 also. So whatever, if it is given there, you can consider that only. Okay, so stopping potential is related with the frequency and everything. So let me write, the kinetic energy is h into hc by lambda minus phi naught. This is how we write. And this we can write, the kinetic energy is my E into V stopping. So this becomes my hc by lambda minus phi naught. Now what is the condition? If the work function of the metal is this and stopping potential is 2 volt, what is the wavelength of EM wave? Okay, so stopping potential is 2 volt. Okay, so E into 2 volt. Okay, this is hc by lambda minus what is that, 2.14 electron volt. So here if I am putting this as 2 volts, okay, if I am putting this as 2 volts, so 2 into E is in the SI units, okay, that is in the SI units. I need to convert that to electron volt. So to convert that into electron volt, what I will do, how to convert that? Joules to electron volt, divide that with E. So that E and E will get cancelled. So this basically becomes 2 electron volt. So 2 electron volt here, this is 2 electron volt here, plus 2.14 electron volt here, and this is equals to Hc. Hc, let us write this as in electron volt and nanometer. So this is 1242 divided by 1242 divided by lambda, and lambda I will take in nanometer. Now this equation is simplified. Is this clear? Let me write it like this. This is 2 into E and this is in SI. Okay, if I talk about this is in joules, this is in joules. I need to convert this into SI unit, but how will I convert that to SI unit? Divide by 1.6 × 10 to the power 19. So divide with E. So this will become 2. Unit will be electron volt. This is also electron volt. So this electron volt, this becomes 4.14 electron volt. So I got 4.14 electron volt is coming out to be 1242 divided by lambda in nanometer. Okay, so this becomes here 300. Okay, so lambda comes out to be 300 nanometer. 300 nanometer, that is option D. Got it? Understood it? If you are having any doubts in any of the points or you need some more clarity, you can mention in the comments. Okay, so I am available in the comments. So if anything you are mentioning about this video or any query in any of the place, make sure you mention in the comments. I'll get back to you. Next thing, when a metal surface is illuminated by light of wavelength lambda, the stopping potential is 8 volt. When the same surface is illuminated by wavelength of lambda 3 lambda, stopping potential is 2 volt. The threshold wavelength of the surface of this surface is. How to relate the threshold wavelength? We know h mu naught, this is equals to my work function. So mu naught is basically equals to phi naught by h. So I need work function. If I need work function, I can relate the threshold wavelength. Now let us write these two equations here. Initially the stopping potential is 8 volt. Okay. So let me write the kinetic energy is equals to Hc by lambda minus phi naught, and this is equals to E into V stopping. So V stopping is given as 8 volt. So Hc when the wavelength is lambda. Okay. So first equation will be Hc by lambda minus phi naught, and this is equals to 8 into E. This is my first equation. Second equation is when the wavelength becomes 3 lambda, the stopping potential is 2 volt. So this is 2 into E when this lambda becomes 3 times of lambda. So Hc by 3 lambda minus phi naught. These two equations are there. So what I can do is I need phi naught. I need phi naught in terms of Hc by lambda. Okay. So from here this 2E. Okay. So from there you can say this by 8 is this. Okay. This whole by 8 is my E, or this whole by 4 you can equate like this. So let me write it again. This is my first equation. This is the way of simplifying. Anyways, you can simplify by any of the methods. So what it is now, Hc by lambda minus phi naught. This is what? Hc by lambda minus phi naught. It is 8 times of E. So this is 2E. Multiply this with 4. Multiply this with 4. So 4 times of Hc by 3 lambda minus phi naught. Is this clear? Are you able to understand it? Okay. So from here I can say therefore phi naught will be here, here will be having phi naught only, and 4 plus 1 5 phi naught will become on the other side. So 5 phi naught comes out to be 4 plus sorry, I did a mistake. This is minus phi naught, this is minus 4 phi naught. I need to take on this side. So 4 minus 1 will be 3 phi naught. So 3 phi naught will be equal to 3 phi naught will be equal to I'll take this on other side. 4 by 3 minus 1 is 1 by 3. 4 by 3, you know, this is 4 by 3 hc by lambda, this is hc by lambda. 4 by 3 minus 1 is 1 by 3. So hc by 3 lambda. So phi naught from here is getting hc by 9 lambda. Now put phi naught here. Put here. So phi naught is hc by 9 lambda. So mu naught is equals to phi naught as hc by 9 lambda, hc by 9 lambda divided by h. Okay. Now what is mentioned here? Threshold wavelength is mentioned. Okay, not threshold frequency. So threshold wavelength, that will be my c by lambda naught. Okay, so this is c by lambda naught. So c by lambda naught is c by 9 lambda. Okay, so this I will write as c by lambda naught is equals to c by 9 lambda. So my lambda naught comes out to be 9 lambda. Option C. Question was very straightforward. Now from here, if you see, there are very less things that you can ask. You know, only one equation is there. What you can ask from that? You know, hardly, you know, sometimes you will give kinetic energy, sometimes you give the stopping potential, sometimes you relate the threshold wavelength with the stopping potential. Only these type of things, isn't it? Next question. Which of the following shows the correct variation of applied potential difference V with photoelectric current I at two different intensities? Okay, so if intensities are different, frequency is same. If intensity is different, it means the stopping potential will be same. So stopping potential has to be same. Here it is different, here it is different, here it is different, here the stopping potential is same, and certainly intensity I2 is greater. So at saturation, the current, the corresponding photo current for I2 will be higher as that of the I1. So, and we have discussed this same thing. So C is the correct option from here. Next thing. Given figure shows a few data points in photoelectric effect experiment for a certain metal. Minimum energy for ejection of electron from its surface is. Minimum energy for ejection. How much minimum energy you need to give? Can you please tell in the comments? You can pause the video. Can you tell in the comments what is that minimum energy needed to give to the electrons? Work function. That is the work function. Yes. So he is basically talking about the work function. Can you relate the work function with the threshold frequency? Yes. We know work function is equals to h times of the threshold frequency. Threshold frequency means where the stopping potential is 0, electrons are just coming out with 0 kinetic energy. Stopping potential is 0, so this is my threshold frequency. 0, na, isn't it? Yeah, this is my stopping potential is 0 there. Okay, yeah, why stopping potential we are taking on y, so y is 0 here. Yes, they mentioned it to be 0. So this is basically my threshold frequency. This is basically my threshold frequency. .5 into 10 to the power, this is a multiple of 10 to the power 14. So into 10 to the power 14 you need to write there. So let us do this. So I will say that my phi naught, is that given in electron volt? Yeah, that is given in electron. We need to convert that also. So phi naught is equal to h, that is 6.6 into 10 to the power minus 34 into mu. What is mu? 5.5, the mu naught. Okay, this is my mu naught. That is 5.5 into 10 to the power 14. This will give the answer in joules. We need to convert this to electron volt. So divide this with 1.6 into 10 to the power minus 19. Now this answer will be in electron volt. 19 plus 14, what it will become? 33. Yeah, and this is minus 34. So only 1 by 10 will remain, that will come in the denominator. So 6.6 into 5.5 divided by 16, and now this is the answer in electron volt. Let us see how much it is. So this is 6.6 into 5.5 divided by 16. 2.268, so that is 2.27, option B. Now let us discuss about wave nature of matter. So de Broglie thought one thing, that nature loves symmetry, isn't it? Yes, nature loves symmetry. If light is behaving like particle also and wave also, generally you can say the more predominating nature of light is the wave nature. So light is behaving like particle also, light is behaving like wave also, then it should be possible for the particles also to behave like a wave. Opposite should also happen, na? Isn't it? Like the same funda. If there is magnetic field, if there is electric field due to change, due to change in the magnetic field, the magnetic flux, okay, there should be corresponding magnetic field due to the change in the electric field. Uh, that was Maxwell's thing. You remember that, displacement current and all. So if there is electric field induced due to change in magnetic field, there should be some induced magnetic field that should come due to electric field. So same thing here. If there is wave and particle nature of light, if the light can behave like a particle, then the particle must also behave like a wave. Yes. Yes, that was de Broglie hypothesis, and this was, you can say, shown in the Davison and Zermer experiment also. We will talk about that. So certainly, if you talk about the associated wave with the particles of very high mass, okay, so that is, you can say, not there. Specifically here we talk about very small particles, okay, very small particles. For those particles, because in de Broglie hypothesis, okay, so for photon, if I talk about what was the momentum, P is equals to h by lambda. This is how we write for photon. Okay, this is my momentum. This is my momentum. Okay, this is I am talking for photons. This is how we write. So for particle also, my momentum P, what is that? That is mv. That is equals to h by lambda. So the corresponding lambda comes out to be h by p or h by mv, where p is the momentum. Okay, so this is my de Broglie wavelength. Okay, this is my de Broglie wavelength. If mass is very high, or you can say if the mass is high, then this lambda will be very small. Lambda will be very small. Therefore, when we talk about the associated wave, you can say associated wave with the particle, there we talk about, very small particles, specifically electrons, protons, like that. So this wavelength we call as the de Broglie wavelength. This is my de Broglie wavelength. So remember this formula, de Broglie wavelength is equals to h by mv. Now here you will have a particle, let us say an electron is there, which is accelerated through a potential v, and then tell us the corresponding, you can say, associated wavelength or corresponding de Broglie wavelength. Then what you can do, just you can relate with the kinetic energy and all. So this is my momentum. Momentum I can relate with kinetic energy. Okay, so mv, because we know half mv square is my kinetic energy. Let us write that as k. So from there I can say mv comes out to be root of 2 into k into m. Okay, multiply both sides with m, take this 2 there, root of this, that will become root of 2 into k into m. So I can write this lambda as h by mv. I can write this as h by root of 2 into the kinetic energy into the mass. Now if there is some particle which is accelerated through a certain potential V, how much kinetic energy it will get? Charge into the potential. Okay, so there we will put this kinetic energy as charge into the potential. So this I can also write as is equal to H divided by 2, this kinetic energy V into Q into M. Okay, if that charge particle is my electron, then I'll write this Q as my E. Okay, so this V is my potential difference through which the charge is accelerated. If the charge is accelerated through potential V, the kinetic energy will become V into Q. So I'm putting here V into Q, where this my Q is my charge. M is the mass. M is the mass. Okay, I'm writing M here also, here also, here also. M is the mass. If the charge is given as electron, I'll write Q as E. If the charge is given as proton, that is magnitude is E only. If there is some another particle, let us take alpha particle or something like that, we will write the charge of that. So remember this. Now this is Davison and Zermer experiment. So don't go into much detail, we will not talk about very much detail here. So simple thing is, here a beam of electron, okay, here the beam of electron was passed through a single slit experiment. What was that? Diffraction pattern that was observed in case of light. Yes, so same kind of diffraction, you can say, pattern was observed for beam of electron also. Somewhere the intensity was higher, somewhere the intensity was low. Okay, like that you can say, where more number of electrons are reaching, where less number of electrons are reaching, the minima was there. Okay, so like that the patterns was formed here. So this shows the diffraction pattern. Okay, so for light, if I talk about, now we are having single slit and we are having the screen here, and light was incident here. Okay, so here on the screen the diffraction pattern was formed. Okay, diffraction pattern was formed. So same thing. Okay, so same thing was observed here also. Here you can say the beam of electron is coming. Okay, so this is my beam of electron. Okay, and here also my diffraction pattern was observed. Diff I am writing, that is my diffraction. Okay, it means what? It means this beam of electron is behaving like a diffraction pattern. Shows which nature of light? Wave nature, na? Yes, so it means this electron beam is behaving like a wave. That was the conclusion. Okay, so the conclusion is this beam is behaving like a wave. Conclusion is this moving electron. Okay, this moving electron. Okay, so this moving electron is behaving like a wave. Let us write electron beam, so that is understood. So electron beam is behaving like a wave. This is the proof of de Broglie hypothesis. De Broglie have had that hypothesis in mind. This should have happened. This should happen. If that is happening, this should happen. because in nature symmetricity is there almost everywhere. So, and when the experiment was done by Davison and Zermer, this was shown. Yes, it is there actually. Okay, let us discuss this question. An electron of mass m with kinetic energy with initial velocity v naught I cap enters an electric field that is minus E naught k cap. If the initial de Broglie wavelength is lambda, then value after time t, value of what? De Broglie wavelength. So, let me write the initial de Broglie wavelength. What is that? That is given as lambda naught. So, initial de Broglie wavelength lambda naught, that I will say that is my h divided by m into v. This is how we write. Initial velocity is, speed is v naught. So, h divided by m v naught. After time t, velocity will change because acceleration is there. What is the acceleration? Acceleration is electric field into charge is minus e, okay, divided by the mass. This is the acceleration is there. What is E? E is minus E naught k cap. So, this will become E naught into E k cap divided by m. Okay. Yes. So, this becomes my acceleration. So, if I talk about the velocity, how we write velocity? Velocity is u plus at. Acceleration is constant, so I can say anytime the velocity is initial velocity plus acceleration into the time. So, what is the initial velocity? Initial velocity is v naught I cap. So, v naught I cap plus acceleration into time. So, this is E naught E by m into t, and this is k cap. So, if I ask you what is the final speed here, v, you will take that as a root of this v naught square plus this square. So, if I ask you what will be the wavelength, so lambda by h divided by, so lambda dash, so that will be my h divided by m into v. V is root of v naught square plus E naught E t by m square. Okay, lambda naught is h by m v naught. So, let us take v naught out here and this will become lambda naught there. Okay, so lambda, let me write here. Okay, so this will become lambda dash is equal to h by m v naught. I am writing as my lambda naught. So, lambda naught plus root of, this will become 1 here, 1 plus this will become E E t by m v naught whole square. Sorry, E E t by m. This is the new wavelength, and which option? C option is coming. Yes. So, just find the final momentum magnitude we need only. Okay, from there I can write the new de Broglie wavelength associated with it, and from there I wrote it. The de Broglie wavelength of an electron is same as that of a photon. If velocity of electron is this, 25% of the velocity of the light, then the ratio of kinetic energy of electron and kinetic energy of photon will be. Many times the questions in mains are asked. The momentum of the proton and this is same, alpha particle or electron, and find the ratio of the de Broglie wavelength, or the kinetic energy is same, find the ratio of the de Broglie wavelength, or sometimes the relations are given like this. You might have seen such many such questions. Now, let us discuss. De Broglie wavelength of electron is same as that of photon. So, lambda is h by the momentum. It means the momentum of electron is same as the momentum of the photon. Momentum of the photon. So, how we write the momentum of the photon? H by lambda. How we write the momentum of the electron? mv, mass of electron, into the velocity of the electron. If the velocity of the electron is 25% the velocity of light, 25% means 1/4. Okay, so I can say m into c by 4 is equals to h by lambda. This we got. Then the ratio of kinetic energy of electron and kinetic energy of photon. So kinetic energy of electron divided by kinetic energy of photon if I write. Okay, so how we write the kinetic energy of the electron? Either write p square by 2m or you write half mv square, any of the ways you can write. Let me write in terms of momentum, okay, p square by 2m. Kinetic energy of photon hc by lambda. Now this momentum you can write as h by lambda. So h by lambda there. H by lambda and this lambda by h, they are getting cancelled. So I got this ratio as h by lambda into 2m into c. H by lambda I got mc by 4. H by lambda I can write as mc by 4. So this will become 1 by 8, isn't it? Yeah. So this relation we are using there. So this will become 1 by 8. 1 by 8, that is option B. Okay. Next question. The de Broglie wavelength of a molecule in a gas at room temperature is 300 Kelvin is lambda 1. If the temperature of the gas is increased to 600 Kelvin, then de Broglie wavelength of the same molecule becomes. Now, if temperature increases means the velocity will increase. If the velocity will increase means momentum will increase, the de Broglie wavelength will, you can say, change. So how should we relate? So lambda is equals to h divided by mv. This formula we know. If we know this formula, and we know for gas V is proportional to root of T. How? Vrms is equals to root of 3 RT by m. You know that? Yes. So V is basically proportional to root of T. It means mass is the same, mass will remain the same. It means my lambda is inversely proportional to root of T. So my temperature is getting doubled. So lambda will become 1 by root 2 times. Okay, so initial temperature was this, the wavelength was lambda 1. Okay, so if I say my lambda 1 proportional to 1 by root of 300, and if the temperature of the gas is increased to 600, the de Broglie wavelength will be. So lambda, let us take 2, 1 by root of 600, then you take the ratio. So lambda 1 by lambda 2 comes out to be root of 2. So my lambda 2 is basically lambda 1 by root 2. A option is coming. Okay, now we are moving to the next chapter, atoms. So first of all, some basic understanding I am expecting that you are already having. Specifically the J.J. Thomson of the model, J.J. Thomson model was there. Before that Dalton thing was there, okay, smallest unit is atom, that is indivisible, all those things, and J.J. Thomson came, okay, so the plum pudding model was there, okay, whole atom is like, you know, a cake which is positively charged, okay, or you can take an example of watermelon, positively charged, and the negative charges are distributed like the seeds of the watermelon. And then comes the Rutherford model. Now Rutherford did experiment, and this is the famous experiment, the alpha particle scattering. What he did was, he took a gold foil, okay, and beam of alpha particles were thrown at the gold foil. And the interesting thing was, very few of the alpha particles, very few, I'll talk about how much few, very few of the alpha particles was reflected back. And Rutherford was surprised to see that. He thought, it's like, we are shooting a bullet to the paper and the bullet is reflected back. Isn't it? Like you shoot a bullet to the paper and the bullet comes back, you know, from the paper like that. You will be surprised like how this can be possible. How this can be possible. Although it happened very rarely. Okay, let us take from 1 crore or 1 billion of a bullet, one bullet came, but still you will be surprised. Yes, how this is possible. So same thing happened with Rutherford, and then eventually Rutherford draw many conclusions from that, and this was the discovery of presence of nucleus, whole positive charge that is concentrated at the center. Almost all the mass of the atom is at the center, most of the space is vacant. These type of things were concluded. Okay, so this was the setup. Okay, so here the alpha particles are coming and this is my gold foil. Okay, so most of the particles from the beam, they pass directly straight. Why so? Most of the space is empty. Very few were deflected and some very rare were reflected back also, like that. So these were observed. Now you see, these are number of scattered particles detected. So those who had deflection less than 0 degree, that is very high. And as we are talking about 20 degree, 40 degree, 60 degree, 100 degree, 120, 140, 180, 180, this number is very, very less as compared to the original number. Okay, so deflection was there but very few. Okay, very, very rare particles, very, very few particles were deflected to obtuse angle, very few. So some conclusions: most of the alpha particles passed through the foil without any deviation, no deviation. What was the conclusion from this statement? Most of the space in the atom is vacant. About 0.14% of the incident particle scattered by more than 1 degree. 0.14%, not 0.14 fraction, percent means how much is the fraction? 0.0014. Very, very small, isn't it? Yeah. So 0.0014 fraction had a deviation more than 1 degree. I'm talking about. Next is deflection of more than 90 degree was observed in about 0.0125% of the incident particles, more than 90 degree. Then most of the space in the atom is unoccupied, okay, as about 99.86% alpha particles passed without deviation. So no deviation was there, it means nothing was there. No deviation was there, they passed straight. If they passed straight, it means that space was vacant or that space was empty. Therefore, and how much is that space? This much percent of the space is vacant. It means only 0.14% was having something. Yes, there must be extremely small region of the concentrated positive charge. Why positive charge? It was deflecting. Okay, some of the particles were even reflected back. It means there is some positive charge which is repelling this positive charge of the alpha particle, then only it is possible. So that was clear from there. So positive charge at the center of the atom. This small region is called the nucleus. Now this was the discovery of nucleus. The scattering of alpha particle is due to encounter between the alpha particle and the nucleus of the atom. This we got. Next is the nucleus of the atom is so massive as compared with the alpha particle that it remains at rest during the encounter. It was very massive as compared to the alpha particle. So whole of, you can say, the mass was there in very small, you can say, fraction, where the electrons owing to their little mass cannot appreciably deflect the far more massive alpha particle. Anyways, next, electrons revolve around the nucleus in orbits like planets revolve around the sun. But there is a glitch. There is a glitch in this statement, and due to that glitch, you can say Rutherford model was having a major limitation, and that limitation was of stability. We'll talk about that. When alpha particle strikes the metal foil, it can penetrate the outer electron cloud and approaches the nucleus closely. Then it moves under the action of the Coulomb's force of repulsion, and the path is hyperbola. And the nucleus, okay, hyperbolic path is there. That you already know in gravitation. If something is coming from infinity, which is already having some energy, okay, let us take some mass from infinity is, you know, coming towards sun, and it is already having certain energy. So when it will, you know, due to sun's gravitation, certainly its path will be deflected. That deflected path will be hyperbola, because that is not bound to the sun. Therefore that path is hyperbola. If that is bound, that will be elliptical kind of thing. Let us take the path of a planet. If a planet is there that is bound to the sun, that will be elliptical. If that is not bound, the path will become hyperbola. Okay. Now, let us take, this is my atom. At very small portion, there is the nucleus at the center. So this is my nucleus. Alpha particles are coming, okay, from here. If some alpha particle is coming like this, deflected like this. Okay, some alpha particle is coming like this, deflected like this. Okay, some alpha particle is coming like this, deflected like this. If some alpha particle is coming like this, okay, head on, coming like this, stop here, and then it will go back. So specifically here we are talking about this particle which is coming head on, okay, here to the nucleus. So it will come like this. This nucleus is positively charged, this alpha particle is positively charged, so here it will stop. At this point my velocity will become 0. So this separation, let me take the dotted one, dotted lines, dashed lines, okay. So this separation we call as the distance of closest approach. Let us represent this with R naught. So this we call as the distance of closest approach. It was having certain velocity, coming like this, okay, head on. Here it will stop, positive charge, they are repelling. It was slowing down. Eventually it came at rest. It cannot be reflected because it is just pointing towards the center. But now this case is very rare. Why this case is very rare? Because, you know, most of the space is empty, only 0.14% is there, you know, in which the nucleus is there. So it has to hit directly head on that, okay. So that is, you can say, a rare thing, okay. So distance of closest approach. Now let us relate this distance of closest approach with the initial kinetic energy of the electron or the speed of the electron. So let us take initially at this is my condition 1, okay, here this is my condition 1, and here this is my condition 2. This is my condition 2 here. This let me write 2 here. This is my condition 2. Total mechanical energy will be conserved, okay. So initial kinetic plus potential, okay, I am applying conservation of mechanical energies come, okay, conservation of mechanical energy. So initial kinetic energy plus my initial potential energy is equals to final kinetic energy plus my final potential energy. Here I'll be taking electrostatic potential energy because that is way more as compared to the gravitational potential energy. Initial kinetic energy, it is here having some kinetic energy, let us take K, plus initial potential energy, this was at a long distance, considering this to be, you know, infinity, initial potential energy is 0, is equals to final kinetic energy, it stopped at this distance of closest approach, so final kinetic energy is 0. Final potential energy is This is the separation between the two charges. This if atomic number is Z, so this charge is plus Ze. Let us use a different color. If the atomic number of the nucleus is Z, so this is plus Ze. Okay, and of the alpha particle, how much is that? How much is the charge? Plus 2. Okay, so this charge is plus 2 for the alpha particle. So K Q1 Q2 by R, this is how we write the potential energy. You remember this formula? Do you? So K Q1 Q2 divided by R naught, and this become my K is 1 by 4 pi epsilon naught Q1 Q2. So this Q1, any you can take Q1, any charge you can take as Q2. So this is Ze into 2E divided by R naught. This is my kinetic energy K. So this kinetic energy K comes out to be 2ZE square divided by 4 pi epsilon naught R naught. So R naught I can write, if you have to find this R naught, so R naught I can write from here as ZE square divided by 2 pi epsilon naught into the kinetic energy. Sometimes velocity is related, so you can write the kinetic energy as half mv square. If you have to relate this with velocity, write it like this. This distance of closest approach question was asked 2026 this year, okay, in January attempt. Okay, got it? Let's do some questions now. First question on Rutherford model we are having. The graph which depicts the result of Rutherford gold foil experiment with alpha particle is this. Theta is scattering angle, y is number of scattered particles. So number of scattered particles are very rapidly decreasing like this, and we saw that graph, so we will directly say A is the correct option. And this question was asked in 2020. Sometimes, you know, free marks are distributed to everyone. So sometimes, you know, it's very difficult to make it incorrect unless until like you are what should I say, too foolish. It's very difficult to make few things wrong, specifically this. So you cannot do this question wrong, isn't it? Okay, next. In an alpha particle scattering experiment, distance of closest approach for the particle is this. If target nucleus has atomic number 80, then maximum velocity of alpha particle is this. So how we related? You remember that? I don't remember the formulas, by the way. So I'll just write half m v square is equals to k, that is my 9 into 10 to the power 9, anyways, 1 by 4 pi epsilon naught k q1 q2. So z into 2 e square divided by r, k q1 q2 divided by r. And this is the same thing here, same thing, I'm writing it again. From here I need to relate with the velocity. So this 2 into 2 into 2. So velocity will become, what should I write here? Velocity will become root of, what I need, by the way? Yeah, velocity only I need. So root of, this is ZE square divided by, m will come here, pi epsilon naught r into m. Now you can multiply and divide with 4. I'll prefer to do that. Why so? Why so? Because 1 by 4 pi epsilon I can directly write as 9 into 10 to the power 9. Therefore, I am multiplying and dividing with 4 here. Rest everything is fine. Okay, now put the values. Let us put the values. 4 into z, what is z? Z is 80 e square 1.6 square into 10 to the power minus 38 it will become, okay, divided by 4 pi epsilon naught I already considered, not considered yet, 9 into 10 to the power 9. 1 by 4 epsilon naught is 9 into 10 to the power 9 into r into m. What is r? 4.5 into 10 to the power minus 14. Minus 14 into what is the mass of the alpha particle? That is 6.72 into 10 to the power minus 27. Seven kg. Okay. Yeah. Now let us first of all take all the 10 to the power together and try to simplify it. It is 14. 14 plus 27 it will become 41. 41 when it will go in the numerator, 10 to the power 3 will remain here. 9 plus 3 is 12. 10 to the power 12 root will become 10 to the power 6. So 10 to the power 6 into root of 4.5 into 2. So 4 into 80 into 2 into 1.6 square into 2 divided by 6.72. This is what is coming. Let us see. 4 into 80 into 1.6 square into 2 divided by 6.72, and this we have to take whole root. So this comes out to be 1. This comes out to be 10 to the power 6 into 15.61. 15.614 like that. And here we have to report in 10 to the power 5 approximately. 10 to the power 5 you do, it will become 156.14, and if you round it off it will be 156. Clear? Easy? Getting it? That's great. You see, it's difficult to interact in recorded video. Bohr's model of hydrogen atom. Now, first of all, let us talk about the issues with the Rutherford model. I didn't mention in the theory, but I'll talk about here. So, the major issue with the Rutherford model is of stability. It could not, define why the atom should be stable. Electrons are moving. Okay, electrons are accelerated. If a charged particle is accelerated, it will what it will do, according to electromagnetic theory, it will emanate electromagnetic radiations. So electromagnetic radiations will come. It means the energy of the electron will decrease. As the electron energy will decrease, slowly it will collapse at the center with the nucleus. Okay, means let me write here the thing, limitations of Rutherford model. Yeah. Limitations. You should understand I am talking about Rutherford model. Okay. So the main limitation is stability. Stability, or I should say, could not define how an atom could not define how an atom is stable. Thing is, yes, he got that nucleus is at the center. Yes, he got the electron is revolving around it. Okay. This is my electron. It is revolving around it. This is accelerated. So if this is accelerated, it will emanate the electromagnetic radiations. Okay. Why? Because this is accelerated as charged particle. Is accelerated. It means what? The energy will decrease. If some energy is emanated, what should happen? Energy of the electron will decrease with time. Yes, it means energy of the electron decreases. If the energy of this electron will decrease, what will happen? Slowly it will go like this and it will collapse with the nucleus. It will collapse with the nucleus, atom will not exist. Okay, existence of the atom, you can say, is not proved. So this Rutherford model could not explain why an atom is stable. Simple thing. Okay, now there comes Bohr's model. So Bohr's, first of all, the first point was, the pinpoint was the stability. So Bohr was smart, Now first I have to address this stability thing. So he addressed that, and postulate one he did. Okay, he made three postulates. So the first postulate, he mentioned that electron in an atom could revolve in certain stable orbits without emanating radiant energy. This is the most important thing. Highlight it. Okay, he addressed this. He addressed there are certain stable orbits which are existing, and in those stable orbits, if an electron will move, it will not radiate any energy, and these orbits we call as stable orbits. Okay, first thing is these orbits we call as the stable orbits. So each atom has certain defined stable orbits. Electron can exist in these orbits. Each possible orbit has defined total energy. These stable orbits are called the stationary states of the atom. And there we gave, okay, this is the first state, this is the second state, this is the third state, and is equals to 1, 2, 3, 4, 5, like that. Okay, so these are my stable states. If the electron is there in these stable states, no energy will be emanated, no loss of energy will be there, the atom is stable. So the first postulate exactly addressed that pinpointing thing in the Rutherford model of instability. He addressed, yeah, this is the reason why the atom is stable. Okay. Second is, an electron can revolve around the nucleus in an atom only in those stable orbits whose angular momentum is integral multiple of h by 2 pi, where h is the Planck's constant. Therefore, angular momentum of the orbit electron is given as n times of h by 2 pi, where n is equal to 1, 2, 3 for first orbit, second orbit, third orbit, like this. Now you may ask, sir, why? Why only nh by 2 pi? Okay, he didn't mention that. But later on, de Broglie, after you can say almost 10 years after Bohr mentioned, okay, give these postulates, after that he explained actually why this has to be integral multiple of h by 2 pi. That will come in a while. Okay, so that was proved by or that was explained by de Broglie basically. I'm not explaining right now this thing. Okay, this is the integral multiple. Angular momentum is integral multiple of h by 2 pi, and angular momentum I can write as mvr. M is mass of the electron, v is the velocity of the electron, r is the radius of the orbit, and that is equal to nh by 2 pi. Keep this thing in mind. The third postulate, simple energy conservation. An electron can make transition from its stable orbits to another lower stable orbits. While doing so, a photon is emitted whose energy is equal to the energy difference between the initial and the final state. Therefore, the energy of the photon that will be emitted will be equal to initial energy minus the final energy, and that is equal to h into mu. Simple thing. Like, let us take these levels are there. Okay, so from initial, let us take this is my initial, this is my final. So let us take the electron goes from some higher orbit, okay, to some lower orbit. So then what will happen? Its energy decreases. Where that extra energy will go, that will be released as a photon. So here it will emit a photon, and the energy of this photon will be equal to the difference between these two energies, E initial minus E final. Opposite also can happen. This electron can absorb a photon and it can excite to a higher energy state. Okay, how much energy it will take? Same, the difference between the two. Okay, so this is the third postulate. Now let us discuss this model in detail. So model for one electron species. So keep this thing in mind. Bohr's model is only applicable for one electron species. That is a major limitation. And why this limitation is there, you will understand in a while. Okay. So first of all, let us apply Coulomb's law of attraction and all. So my nucleus is there. Let us take the atomic number as Z. So the charge is plus Ze. Around this, the electron is there at some distance r. Okay, let us take the radius as r here. Let me take a dotted line. I should make a better diagram. Is it required? I think you'll understand from this. Let us take this radius as r. Okay. Now on this electron, one force is, there is only one force, and that is due to this positive charge. That is my electrostatic force. So this force is equals to mass into the acceleration. Simple thing. Okay. This force F is equals to mass. This is moving in circular orbit. Okay. So mass into the acceleration. What is the acceleration here in circular orbit? Centripetal acceleration. Okay. Its velocity is in this direction, v. So its acceleration is centripetal acceleration towards the center. So it is having a centripetal acceleration towards the center. So this is mass of the electron into the centripetal acceleration, and this centripetal acceleration we can write as v square by r. What is this force? Force we can write as k q1 q2 divided by r square. So k q1 is plus Ze, q2 is minus e. So just magnitude I am writing into e. Okay, let us write properly. So k into q1 is Ze into q2 is e, just writing the magnitude. Okay, it is attractive in nature due to the negative sign. So k q1 q2 divided by r square, so r square. This is my first equation. Second thing is, I know the angular momentum is nh by 2 pi, so I can say from second postulate mvr is equals to nh by 2 pi. From these two equations, let us simplify for r and v. Okay, so if I simplify this equation further, this will become k z e square, k I am writing as 4 pi epsilon naught. Okay, so z e square divided by k as 1 by 4 pi epsilon naught. So 4 pi epsilon naught r square, this is r, 1 r will get cancelled, r will remain here. This is equals to m into v square. From here, I can put the value of r in this, get the velocity, or from here, I can put the value of v in this, get the radius. Anything I can do. So let us put the value of v. So from here, this is my first equation, this is my second equation. Let us write v. So v is equal to nh divided by 2 pi m into r. Let us put it here. So this is mv square. So n square h square divided by 4 pi square m square r square. Is this clear? Yes. Is equals to this. This is z e square divided by 4 pi epsilon naught r. Now, here I can cancel few of the things. 1 r is getting cancelled. Okay. What else? 4 pi, 4 pi, 4 this pi. What else? 1 m is getting cancelled. This got cancelled. Is there anything else? I don't think so. Okay. From here, let us write what is r. So from here I can say my r, I'll take this r here. So r comes out to be what it will become? N square h square, n square h square divided by z e, okay, epsilon naught will also be there, epsilon naught will go there, epsilon naught divided by z e square by m. Okay, so this thing I can write as, or should I write here? This r as some constant. Now my n can vary, my z can vary. Anything else? H is constant, epsilon naught is constant, E is constant, mass is constant of the electron. So all the constants, let us take them together. So this will become h square epsilon naught divided by h square epsilon naught divided by E square into pi m, E square into pi m, and this whole into n square by z. Okay, now this is a constant. I can write this constant as my r naught. So this becomes my r naught into n square by z. This r naught will be the radius when n and z both will become 1. It means the first hydrogen, Bohr's orbit for the hydrogen atom, the radius of first Bohr's orbit for the hydrogen atom. Okay, that is my r naught. And you can put value of h. H is 6.6 into 10 to the power minus 34 square into epsilon naught 8.85 10 to the power minus 12. E is 1.6 in 10 to the power minus 19. Pi, you know, that is 3.14. Mass is mass of electron, that is 9.1 in 10 to the power minus 31. So you can put these values, you can solve for r naught. So what r naught will come out to be here is 0.53 into 10 to the power minus 10 means angstrom. Okay, so this comes that this much angstrom. Okay, this is z. Yeah, so keep this relation in mind. Don't go for these things. Okay, don't remember this. I also don't remember. If I have to write, I can quickly write. Don't remember this. Remember this. This is required. 0.53 into n square by z. Sometimes up to 3 decimal places it is right. 0.529 like that. Remember it, 0.53. So 0.53 into n square by z angstrom. This becomes my radius of nth Bohr orbit. Keep this in mind. This is radius of nth Bohr orbit. What is 0.529 or 0.53 angstrom? That is radius of first Bohr's orbit for hydrogen. This R naught thing. Okay, so this becomes my radius of nth Bohr's orbit. Now put this R here and solve for velocity. Let us do this. V is equals to NH divided by 2 pi m into R. What is R? R is this. Put this term. So this is h square epsilon naught n square, h square epsilon naught n square, h square epsilon naught n square divided by this whole. So divided by this whole means E square pi m into Z. E square pi m into Z. So this simplified like this. Let us see what all things can be cancelled from here. This n is getting cancelled. What else? This pi is getting cancelled. H is getting cancelled. M is getting cancelled. I don't think anything else is there. Okay. Now let us write the velocity. So V comes out to be, what is the constant terms? Z by n are variable. I'll take that out. So this will become E square divided by 2 H epsilon naught. E square divided by 2 H epsilon naught. And this Z by n I'll take out. So this becomes my V naught. This is a constant, it will not change. Z by N and will change. So this becomes my V naught. V is equals to my V naught into Z by N. What is V naught? Speed of the electron in the first orbit of hydrogen atom. Okay, and this value comes out to be 2.18 into 10 to the power 6 Z by N meter per second. Remember this. Okay, remember this thing and this thing. You may not remember the exact these things. Okay, I don't want you to remember the z square by 2h epsilon naught, and that is not required. Remember it. First thing, the most important thing to remember is the proportionality, that v is proportional to z by n, radius is proportional to n square by z. This is the most important thing. Next is this value that is needed, nothing else. Just understand other things. Okay, now let us write the energy. So we wrote radius, we wrote the velocity. Now let us write the time period first. Before energy, let us write the time period. So we talk about the time period. So time period of revolution is 2 pi r. This is the total path length divided by the speed. This much the time it will take. Okay, now I am writing the proportionality. R is proportional to n square by z. Velocity is proportional to z by n. So from here I got the time period is proportional to n cube by z square. This is the important thing to remember. If you have to write the value, you know the value for r, you know the value for v. You can quickly calculate. Don't remember it separately. Next is the frequency. Frequency is 1 by time period. Frequency we know that is 1 by time period. So I can say my frequency is proportional to z square by n cube. Okay. Now I need to talk about the energy also. Let us talk about the energy. First of all, let us talk about the kinetic energy. So how we write the kinetic energy of a particle? Half mv square. Okay. So for electron, if I write, I'll say kinetic energy in nth orbit or in any orbit, it is just simply half mv square. Now I need the expression for v. For v, I have derived that. Let us use that. What is this? This E square by 2h epsilon naught into z by n. So E square by 2h epsilon naught into z by n square. Okay, so if I write it, what it will become? It will become mass is m e to the power 4 divided by this 2 and this 4 here, this will become 8. So 8 h square it will become, isn't it, like h square? Yeah, epsilon naught square, and here z square by n square, proportionality will be there. This becomes my kinetic energy. Okay, now let us write potential energy. potential energy between the electron and the nucleus. How write potential energy for two charges K, Q1, Q2 by R? So if I write the potential energy, that is K, Q1, Q2 divided by R. So K is 1 by 4 pi epsilon naught. Q1 charge of the nucleus plus ZE, charge of the electron minus E divided by R. So what is R? What is R that we had derived? Where it is? This thing. This is h square epsilon naught by E square pi m into n square by z. So h square epsilon naught into E square by pi m. H square epsilon naught into E square by pi m. Sorry, I did a mistake. What was that? H square epsilon naught divided by E square into pi m. Okay, I was writing right. Okay, so E square pi m into n square by z. So n square here it will come, z will come here. Now it looks fine. Okay, now let us simplify it. M will come here, m into e to the power 1, 2, 3, 4, e to the power 4, m e to the power 4, and then pi is getting cancelled by the way, and then I am having z square, a negative sign is there, divided by what I am having, 4 epsilon naught h square into epsilon naught square. Okay, yeah, 4 into h square into epsilon naught square, okay, into n square. See this and this, isn't it? This is twice in magnitude as that of this, and this relation, the proportionality of z square by n square is maintained. You can write this separately. This part into the proportionality of z square by n square is maintained here. Okay. So now we're writing the total energy. Now write the total energy. So if I write the total energy, is sum of the kinetic energy and potential energy. So E is kinetic energy plus potential energy, and this is kinetic and this is potential. If you add them, minus of that it will become. So minus of m e to the power 4 divided by 8 h square epsilon naught square into z square by n square. Okay, now this term is a constant. Okay, and if you find that value, it will come out to be 13.6. So this will become minus of 13.6 electron volt. Okay, everything will be in electron volt. So I can say minus 13.6 into z square by n square electron volt. This is very, very important. That the energy of nth orbit Bohr's model is minus of 13.6 into z square by n square electron volt. If you talk about the energy of first orbit of hydrogen atom, that is minus 13.6 electron volt. And one more thing, if you see the ratio of kinetic energy to potential energy to the total energy, this is 1 is to minus 2 is to minus 1. So my kinetic energy is to potential energy is to total energy. This ratio comes out to be 1 is to minus 2 is to -1. The same ratio was in satellite case also. Same thing. The same ratio was there also. Sometimes the questions are asked from this. Okay, so easy. You have already understood in gravitation. Now you are seeing it here. Okay, is that clear? Now, let us talk about the binding energy or the ionization energy. Now, is the electron free? Certainly electron is not free, it is having some negative energy. If you have to make that electron free, you need to provide same amount of energy so that it will leave, okay, minimum energy, okay. The same amount of minimum energy you have to give. Thank you. So that minimum amount of energy that you have to give such that the electron is freed, that we call as the binding energy or the ionization energy. So it will be mentioned, you know, that find the ionization energy for this orbit or like that. If nothing is mentioned, take from the ground, that the electron is in the ground state of that. Okay, so I'll say the minimum energy minimum energy needed to free the electron. Or sometime it is mentioned a minimum energy needed that should be given to the electron such that the electron will go to the infinity. Yeah, the same thing. So how much is that? It is having some negative energy. Now you have to apply the same amount of positive energy you have to give, that becomes the binding energy or the ionization energy, same thing. Okay, so if I say my binding energy for any electron, that is 13.6 into Z square by N square electron volt. Same thing, binding energy or the ionization energy. Okay. 13.6 into Z square by N square. It was having minus 13.6 Z square by N. Same amount I supplied, it will become 0. Now it is free. If I give some extra energy, it will have its kinetic energy. Now excitation energy. If an electron has to be excited from lower energy state to higher energy state, now how much energy you need to supply? That is the meaning of excitation energy. Okay, so let us take, these are the different levels. Okay, so the electron is, let us take at this initial level, and you have to excite it to this final level. The electron is here, you will give some energy to this electron, the electron will go to this level. How much energy you need to supply? Equal to the difference between the two levels. Okay, energy of the difference between the two levels. So here I say my delta E that you will need to supply is my final energy minus the initial energy. Now I can write this in the complicated terms, or I can just write in the magnitude form, like, you know, minus 13.6 and all. So I can say this final energy is minus 13.6 into Z into my Z square by N square. Okay, so Z square divided by N final square electron volt minus, let me write it here, the space is less. So my delta E is equals to minus 13.6 into Z square by N final square electron volt minus 13 points, minus of minus, that will become plus 13.6 into Z square by N initial square electron volt, or you can take the 13.6 term common into Z square as common. So this will become 1 by N initial square minus 1 by N final square. Okay, so this much energy you need to supply. And this, I'll say this is the excitation energy. So sometimes the question comes, okay, how much energy is needed for this electron to excite it from first excited state to third excited state? Now there is a confusion, sometimes many students get confused. First excited state is not the first state. First excited state is N is equals to 2. Second excited state is N is equals to 3. Ground state is not the excited state. Okay, getting it? So let me write for you. So my first excited state, if I talk about, is n is equals to 2. Second excited state is n is equals to 3. Third, if you talk about, it will be 4th. And my first n is equals to 1 is basically the ground state. We call that as the ground state. Is this point clear? This is important. Sometimes student confuse, oh sir, by mistake I took n is equals to 2. It was mentioned second excited state. There you need to take n is equals to 3. Okay, let us do some questions on this. So this, what we have discussed till now, is very important for atom. If you are not doing anything, at least remember these relations for radius, for velocity, the angular momentum, the frequency, the total energy, the difference between the two levels. Okay, so these things you should understand. In a hydrogen-like atom, the energy difference between second excitation energy state and ground state is this. Now, second excited state and ground state means n is equals to 3 and n is equals to 1. Okay, so energy of the third level and energy of the first level. How we write the energy of the nth level? That is minus 13.6 into z square by n square electron volt. Now, my delta E, that is equals to 13.6 into z square, I will take common. My initial square minus final square, it will become 1 by initial square minus. Okay, the hydrogen atom, hydrogen-like atom, the energy difference between the second excited state and the ground state. So, ground state means n is equals to 1, so 1 by 1 square. Second excited state means n is equals to 3, so 1 by 3 square, like this. And this energy difference is given as 108.8 electron volt. Don't get confused that why I'm taking the difference from first and third. No, I'm taking difference between third and first. Negative sign is there, I took that inside. So, from here, this will become 13.6 z square. 1 minus 1 by 9 is 8 by 9. This is 108.8 electron volt. 13.6 into 8 will be, that will be 108. So, my z square comes out to be 9. So, z comes out to be 3. That is option D. I hope this thing is very clear to you. Consider the Bohr's model of hydrogen atom, hydrogen-like atom. The ratio of, okay, so this is 2 times. It should not be there. The ratio of should not be there. The ratio of radius of fifth orbit of the electron in Li 2 plus and He plus S. So, radius is proportional to n square by z. He is talking about fifth orbit of both, means n is same in both. Okay. So, when I say R1 by R2, in this case, it will become Z2 by Z1. What is Z1? Lithium, it is 3. Okay. And for helium, it is 2. So, this becomes 2 by 3. Is this clear why I wrote Z2 by Z1? I am not writing N1 square, N2 square there, because n is say fifth orbit of this and this, means both fifth orbit. So, n is equals to my 5 in both the cases, anyways that will get cancelled. Z, okay, is inversely. So, R1 here Z1 will go, R2 here Z2 will become, Z2 is my 2, Z1 is 3. Another question, the ratio of speed of electron in third orbit of helium to the speed of electron in third orbit of hydrogen atom will be. Okay, so how we relate the speed? V is proportional to Z by N. Now remember it, energy is proportional to Z square by N square. Energy whether it is kinetic or potential or total energy, that is proportional to Z square by N square. Kinetic energy you can write as half mv square. So V will be proportional to root of Z square by N square. So V is proportional to Z by N. We did derivation also, from there also you can understand. So V is basically proportional to my Z by N. Now if V is proportional to Z by N, in both the cases what is N? Third orbit, N is same. So when I say V1 by V2, this is Z1 by Z2. Third orbit of helium, so Z1 is 2. Third orbit of hydrogen, that is 1. So 2 is to 1. Next question. Hydrogen atom in its ground state absorbs 10.2 electron volt of energy. The angular momentum of the electron atom, of hydrogen atom will increase by the value of. So if it gains 10.2 electron volt, in which state it will go? We need to find. Angular momentum in any state is nh by 2 pi. Initially it was in ground state, so it was h by 2 pi. I need what will be the value of n, okay, final principal quantum number, okay, to which level it will go if it absorbs 10.2 electron volt. So for hydrogen atom, how we write the energy? Energy we write as minus 13.6 into z square by n square. Z is 1. Okay, so Z is 1, so minus 13.6 by n square electron volt. So for n is equals to 1, my energy is minus 13.6 when n is equals to 1. For n is equals to 2, my energy will be, here it will become 4, okay. So this will become minus 4 into 3, so this will become 4 into 3, that is 12, so 1 6 will remain, so point of 4 into 4 is 16, so 0.34 electron volt. What is the difference between these two? The difference here is 10.2 electron volt. It means if the electron absorbs 10.2 electron volt, it will go to the n is equal to 2. Okay. When it will absorb 10.2 electron volt, it will go to n is equals to 2. Initially, it was in the ground state. Here my n is equals to 1. So my initial angular momentum L1 was equals to h by 2 pi, and final angular momentum is equals to n times of h by 2 pi. N is 2 there, so 2h by 2 pi. So how much is the increase in the angular momentum? That is h by 2 pi. This much is the increase. What is h? 6.6 into 10 to the power minus 34 divided by 2 pi, 2 into 3.14. Okay, 2 into 3.14 is 6.28. So it will be nearly 1.05 into 10 to the power minus 34. B option is coming out to be the correct answer here. Simple thing it was. Now sometimes like student get confused, like here angular momentum they are talking, let us do MVR, velocity we write 2.18 into 10 to the power 6 into z by n, let us write r is 0.529, okay, into n square by z, like that, and then eventually calculate. Don't do like that. We know from the second postulate L is equals to nh by 2 pi, so use that directly. Next question, the time period of revolution of electron in its ground state orbit in a hydrogen atom is this. The frequency of revolution of the electron in first excited state will be. Okay, let us relate the time period first and then we will talk about the frequency, because frequency is 1 by time period. So time period we write as 2 pi r by v. This is how we write. R is proportional to n square by z, and v is proportional to z by n. So my time period is basically proportional to, r is n square by z, so n square by z into v as z by n. So this becomes n cube by z, what it is, n cube by z square. When I am solving these questions, or when I am discussing this topic, I try to write everything from basics. Okay, each step I show. Sometimes you may feel like, why the teacher is again writing this relationship. Previously I had mentioned that time period is directly proportional to n cube by z square. So why not directly write and solve? I'm writing each and every step so that, again and again when you see these things, everything will get, into your head. Therefore I'm writing things again and again. Now, the time period of revolution in ground state, we know we need the time period of revolution in the first excited state. First excited state means n is equals to 2. Z is same. So I can say time period is proportional to n cube. If z is same, okay, it is proportional to n cube, n is getting 2, so time period will get 8 times. So my t dash will be 8 times of t. So 8 times of 1.6 into 10 to the power minus 16. 16. Now I need frequency, my frequency there, this much seconds, okay, s is seconds. Frequency there will be 1 by time period. So their frequency f dash will be 1 by t dash, that is 10 to the power 16 divided by 8 into 1.6. How much it will be? This will become 100 divided by 8 into 1.6. Okay, 100 you can write as 25 by 2 into 1.6 or 25 divided by 3.2. That will be nearly 7.8 into 10 to the power 14. Yes, hertz. The unit is hertz, second inverse. This should be inverse minus 1. Is this clear to you? Hope so. You are able to understand everything. Next thing, if the binding energy of ground state electron in hydrogen atom is this 13.6 electron volt, okay, then the energy required to remove the electron from second excited state of Li2 plus is. It means we need energy of the electron in the second excited state of Li2 plus. Second excited state means n is equals to 3. So when we write energy, how we write energy? Energy is minus 13.6 into Z square by n square electron volt. So for second excited state means n is equals to 3 and my Z is also 3. So it will become 3 by 3 square, which will just be minus 13.6 electron. This is the energy of the electron. Need binding energy. Okay, so just take the magnitude of that. Okay, so how much is that? That will be 13.6. So binding energy will become 13.6 electron volt. 13.6 you can write 136 into 10 to the power minus 1, isn't it? Yeah, value of x is 136 then. Next, now magnetic field and dipole moment due to electron, revolution of electron. So electron is revolving. This is my nucleus, and now let me draw a circle using this. So the electron is moving in certain orbit. Let us take here the electron is there. It is moving like this. Let us take. So due to this electron, now a charge is moving in a circle. It means effectively some current is there in the loop. Effectively some magnetic field will be there at the center. Yes. Okay. So we can even find even the dipole moment also, and we can find magnetic field also. So let us do step by step. So first of all, let us talk about the dipole moment. Dipole moment. How we write dipole moment? Dipole moment we write m as NIA, number of revolutions into the current into the area of the loop. Okay, so I can just write I into A. What will be my effective current? Effective current will be charge divided by the time period. Okay, if you take any cross section of this, how much current passes? So you will say in how much time, because there is only one charge only. Okay, so in how much time this will pass, this charge of electron. So charge of electron E divided by my time period. This becomes my current into the area. And time period you can write as 2 pi r by v. So E divided by 2 pi r divided by v into the area you can write as pi into r square. Okay, so from here I can say which things are getting cancelled. Pi is getting cancelled, 1 r is getting cancelled. So this is EVR by, this is EVR by 2. This becomes my dipole moment. And if you have to see the proportionality, V is proportional to Z by N, R is proportional to N square by Z. So basically this magnetic dipole moment is proportional to N. Okay, this comes out to be proportional to N. Now let us talk about the magnetic field now. Here let me write now. How to write magnetic field due to current carrying loop at the center? Mu naught I by 2r. That formula is there in your head. So let me write it. B is mu naught I by 2 into r. Okay. Now how I can write I? Again E by T. So mu naught E by T into 2r. Time period you can write as 2 pi r by v again. So this is mu naught E divided by, time period is 2 pi r by v, like this. So this will become mu naught into E v divided by, this is how 4 pi r square. Okay. And if you talk about the proportionality here, so V is proportional to Z by N, R is proportional to N square by Z, and this is R square, so N to the power 4 by Z square. So this proportionality comes out to be Z cube by N to the power 5. Why I am writing the proportional? Don't remember this proportionality, okay? Don't remember, you know the proportionality of V, know the proportionality for R, okay, so that you can relate. Sometimes in the question you say, you know, due to this the magnetic field is this, now find the magnetic field due to this electron. So that proportionality you should be able to write. Don't remember it, you should be able to write it like this, what I did here. First mu naught I by 2r, I wrote as E by T, T I wrote at 2 pi r by V, and this become mu naught EV by 4 pi r square, V proportionality Z by N, R proportionality is N square by Z. So this becomes the proportionality for B. I am highlighting, but don't remember it. Okay. Now let us do some questions. What is this? An electron revolving in nth Bohr orbit has magnetic moment mu n, and mu n is proportional to n to the power x. What is the value of x? We just did derivation that m is proportional to n, so my x comes out to be 1. I did this derivation, therefore I am just directly writing, otherwise I will be deriving it. I don't, you know, encourage you to remember this. I encourage you to remember the relation for R, for V, okay, for energy, that I encourage you, but don't remember this. This is not needed. Don't remember anything extra in physics. Spectral lines in Bohr's model. Now we know that if you have to excite, or if an electron de-excites from any of the state to lower state, the energy of the photon will be equal to the energy difference between the two levels. Okay, it means that frequency will be some particular frequency, not it's any frequency will be emitted from de-excitation of a particular gas or particular set of atoms. No, you have the specific frequencies. Okay, same thing. If let us take you are bombarding with some electromagnetic radiation, only specific wavelengths will be absorbed, not all the wavelengths, and we can relate what is the wavelength of those specific. Okay, generally when we show the levels, actually we don't show them equally spaced, because the energy difference keep on decreasing. So generally we decrease the space as we show, but I'm drawing it so that visually it looks clear, therefore the space is not that much adjusted. So let us take an electron from some initial level, de-excites to some final level, de-excites like this. Generally we okay, it de-excites like this to some final level. Now here a photon will be released, and the energy of this photon will be equal to the energy difference here. I will say energy of this photon is basically equals to the difference in the two levels. Okay, initial level was having higher energy minus the final level. Now let us put the expression. Let us put first of all how to write the energy of photon, hc by lambda. We know that because I need to find the wavelength. Hc by lambda is equal to initial energy and final energy. I need the expression for energy of nth orbit, energy in nth orbit of the hydrogen. I don't need the magnitude, I need the exact expression, not in terms of 13.6 and all. So exact expression we did here. So here we derived this total energy, and this was coming out to be minus me to the power 4 divided by 8 h square epsilon naught square into z square by n square. So this expression I am going to put here. So this minus me to the power 4 by 8 h square epsilon naught square, this expression, okay, me to the power 4 divided by 8 h square epsilon naught square with a negative sign and into z square by n square. So z square divided by n initial square. Okay. Similarly, when you put final, it will become n final square. So let us take z square common. Initially, inside the brackets, we will have 1 by n initial square and 1 by n final square. So z square I am writing here inside the brackets 1 by n initial square minus 1 by n final square, like this. Okay. N initial is higher certainly, and final is lesser because it is de-exciting. I can take this negative sign inside. So this will become m e square by 8 h square epsilon naught square into z square into 1 by n final square minus 1 by n initial square. And this is my hc by lambda. Again, I can write 1 by lambda expression from here, hc I'll take here. So 1 by lambda comes out to be m e to the power, m e square, okay, hc will come in the denominator. So 8 h cube epsilon naught square into c, okay, this is there, into z square into 1 by n final square minus 1 by n initial square. Now this term, which is m e square by 8 h cube epsilon naught square c, this is a constant. This will not vary. Yes, and this whole constant we call as Rydberg constant. Okay, so this Rydberg constant we write as r, and this 1 by lambda expression comes out to be r z square into 1 by n final square minus 1 by n initial square. this R here is my Rydberg constant. Let me write again here. This R is my Rydberg constant whose value is 1.097 into 10 to the power 7. Okay, keep this thing in mind. And this is in meter inverse. The unit is meter inverse. This is my Rydberg constant. Value. So keep this Rydberg constant value in mind, because you can directly write the corresponding wavelength from here. You can do by other way also, like this term comes out to be 13.6 electron volt, and then you can convert that to joules and do some calculation, but that will be a bit lengthy. So if you can remember value of R here, that's great. And also, if the question is like this, the photon is excited to some higher energy level, how much wavelength of the photon that is needed to excite it? Same formula, use the same formula, because the difference will remain the same, isn't it? Whether it excites or it de-excites, difference will remain the same. So one time it's absorbing, another time it is releasing. So same formula use for that also. Okay. Now these different you can say frequencies or wavelengths are emitted. So all the wavelengths that are emitted when an electron de-excites from higher energy level to the first or the ground state, we call that as Lyman series. When it excites from n is equals to 2, from higher to n is equals to 2, we call that as Balmer series. So here, if the excitation is becoming from any value n initial to final n is equals to 1, we call this as Lyman. Okay. And if it is from any initial state to n is equals to 2, this becomes my Balmer. And if it is n is equals to 3, this becomes my Paschen. Similarly, if it is n is equals to 4, this becomes my bracket, and this becomes my P fund there. Okay. And then now sometimes it is mentioned first line of the Balmer series, second line of the Balmer series. So we call this n is equals to 2 to 1 as my first Lyman series. First line in the Balmer series, second line in the, first line in the Lyman series, second line in the Lyman series, third line in the Lyman series, fourth line in the Lyman series, like that. Okay. So we call this, I'm writing it, here. This is my first line in Lyman. Then this is my second line in Lyman, like that. Similarly for Balmer also, this is my first line in Balmer. Here this is my second line in Balmer. Similarly first line in Paschen. Sorry. Now one thing that is many times confusing to the students is the highest wavelength, the longest wavelength in Lyman series, the shortest wavelength in Lyman series. Okay, these type of things are also termed. For the longest wavelength in Balmer, the shortest wavelength is, now longest wavelength means least energy. Least energy will be for this. So this will correspond to the longest wavelength in Lyman. The shortest wavelength will be corresponding to infinity to n is equal to, because there the gap of the energy will be the highest. Wavelength corresponding will be having the minimum value. Okay. So this is corresponding to the minimum wavelength in Lyman series. Okay, this is sorry, not minimum, maximum, least energy. This is least energy, so this is the maximum wavelength. Yeah, maximum wavelength means the least energy. Maximum wavelength in Lyman series. Similarly, this is my maximum wavelength in Balmer series. And these correspond to the minimum frequency in Lyman, minimum frequency in Balmer. Okay, or I can say this as minimum or the shortest frequency in Lyman. Here this is minimum frequency in Balmer. Okay, now same thing, minimum frequency or maximum wavelength for partition, like that. Now if minimum wavelength, then from infinity. Okay, so if I talk about, let me write here, if I talk about minimum wavelength, okay, minimum wavelength in Lyman, that will corresponding to the maximum energy difference. Maximum energy difference will be from n is equals to infinity to n is equals to 1. Okay, same thing for Balmer also I can say. Similarly, minimum wavelength in Balmer series, so this will be from n is equals to infinity to n is equals to 2. Minimum frequency means the maximum, sorry, minimum wavelength means the maximum frequency. Minimum wavelength here also the maximum. So this is corresponding to maximum maximum frequency in Lyman. This is corresponding to the maximum frequency in Balmer. Okay, so same thing. Let me write here. This can be also my max frequency. Same thing for that, for any of the series. So it's, I wrote these terms because these terms are many times given in the question. So then the students are confused. Instead of doing from infinity to 1, they did from 2 to 1. So these type of mistakes many times happens. Therefore I am writing it. Let us do some questions. During the transition of electron from state A to state C of Bohr atom, the wavelength of emitted radiation is 2000 angstrom, and it becomes 6000 angstrom when the electron jumps from state B to state C. Then the wavelength of radiation emitted during transition of electron from state A to B. Okay, so these states are there: A, B, C. This is A, this is B, this is C. When it goes from A to C, the wavelength is lambda 1, let us take. When it is going from B to C, the wavelength is lambda 2. And when it is going from A to B, this is lambda 3. Okay, and we need to relate lambda 1, lambda 2, lambda 3. Simple thing, simple maths it is, basic maths I will say. This energy will correspond to the difference between A and C. Okay, so E, the energy difference between A and C is equal to energy difference between A and B and between B and C. Okay, for this energy difference, the wavelength of the photon is lambda 1, so I can write this as hc by lambda 1. For this energy difference AB, the wavelength is lambda 3, so this is hc by lambda 3. For this it is lambda 2, so this is hc by lambda 2. Hc is constant, sorry, common from all these three. This get cancelled out and we need to find lambda 3. So from here I can say 1 by lambda 3 is equal to 1 by lambda 1 minus 1 by lambda 2. So I can say lambda 3 comes out to be lambda 2 lambda 1 divided by lambda 2 minus lambda 1. Is this right? Lambda 2 was 6000, lambda 1 was 2000. So 2 into 6, that is 12, divided by 6 minus 2 is 4 into 1000 angstrom. So this becomes 3000. So 3000 angstrom, and the answer is 3000 angstrom. Option D. Simple question. Just apply conservation of energy. Here this energy with not conservation of energy, just the total energy. This total energy is equal to this energy plus this energy. Same simple thing. Okay, if Rydberg constant is R, okay, the longest wavelength of radiation in Paschen series will be Lyman, Balmer, Paschen. Final is n is equals to 3. Longest wavelength means the least energy difference, means initial should be 4. 4 to 3 will be the least energy gap. Infinity to 3 will be the highest energy gap. It means between these two, if it is there, then it will be of longest wavelength. Okay. Now write this 1 by lambda is equals to R into Z. If nothing is mentioned, take Z is equals to 1. He is talking about hydrogen atom. Okay. R into 1 by 3 square minus 1 by 4 square. Just writing the difference. So this becomes R into, this is 9 and this is 16. 16 minus 9 is 7 divided by 16 into 9. This is 1 by lambda. So from here I can say my lambda comes out to be 144 divided by 7R. So alpha comes out to be 144. Alpha comes out to be 144 here. Clear? Next question, if the wavelength of first member of Lyman series of hydrogen is lambda, the wavelength of second member will be. So just I am writing the formula again first, okay. R into Z square into 1 by N1 square minus 1 by N2 square. Now first member of Lyman series. So first member of the Lyman series, first line, okay, first line will be from 2 to 1. So lambda 1 from 2 to 1 I am writing now. So 2 to 1 I am writing. So I will say that my 1 by lambda, that was my lambda, yeah, 1 by lambda is equals to R into 1 minus 1 by 1 square minus 1 by 2 square is 4, 1 minus 1 by 4. So that is 3 by 4. So 1 by lambda is equals to 3R by 4. First equation. And then he is talking about the second member. Second member means from 3 to 2. First is from 2 to 1, 3 to 2, not 3 to 2, 3 to 1. First is from 2 to 1, second will be from 3 to 1. So second member will be from 3 to 1. This is my second member. Now write it. So 1 by lambda is equals to R into 3 to 1 it is coming. So 1 by 1 square minus 1 by 3 square. So this becomes 1 minus 1 by 9. So this becomes 8R divided by 9. This is my lambda dash. Now what I need the value of lambda dash in terms of lambda. So divide these two. This is my second equation. If you divide these two equations, so this lambda dash will come in the numerator. Lambda dash by lambda will become 3R by 4 divided by 8 R by 9. R will get cancelled. So 3 by 4 divided by 8 by 9. This is 27 by 32. So lambda dash is 27 divided by 32 lambda. 27 divided by 32 lambda. This lambda should be in numerator, so you may write it like this, the options. Okay. Wavelength should decrease, energy is increasing, wavelength should decrease. So anyways, the answer will be less than lambda. This is more than lambda. Okay, this is also less than lambda. This is also more than lambda. This is incorrect. This is incorrect among these two. No, two options are there, then we need to solve. Okay. Next. But yes, one more thing you can do, the guess you can do, like, here it is lesser than the half. No, not, it is nearly 1/5. If the energy difference is not 1/5, okay, the ratio of the energy is not 5 there. So it means something else will be there. So just, without doing calculations. A hydrogen atom initially in the ground state is excited by absorbing a photon of wavelength 980. The radius of the atom in the excited state in terms of Bohr's radius A0 will be. Now this photon, it absorbs. I need where it will go. So for that I need how much will be the you can say value of n, to which value of n it excites. So first of all we will find how much is the energy of this. So that I can see this is the energy difference, it will go to this level. So how much is the energy of this photon? So you may write energy of the photon as hc by lambda, and hc thing is given to you here, 12,500. Now don't say, sir, it should be 12,400. If he is saying 12,500, write it as it is. 12,500 electron volt angstrom. Now put your lambda in angstrom. This is 980 angstrom, so 980. How much is this? This is 12,500 divided by 980. So this comes out to be 12.75 electron volt. This is my energy of photon, and basically this will become my delta E. If electron is in the ground state and it absorbs this much energy, to which state it will go? So my energy of the final state will be minus 13.6 plus 12.75 electron volt, and this will be equal to, this is a hydrogen atom only, and this will be equal to minus of 13.6 into z square divided by n final square. How? This becomes the total energy, and that is equal to energy in the final orbit. From there you need to find what is your this n final, how much it is coming. Okay, so this is my 13.6 divided by the difference of this 13.6 minus 12.75. okay, this is how we can do. How much it came? 16. So n final square is coming out to be 16. It means n final is 4. This was in electron volt only. N final is 4. Now I got my n final is 4. The radius of initial radius was A0. What will be the final radius? My radius is proportional to n square by z, or radius of nth orbit is equals to my A0 into n square divided by z. This is how we write. Okay, so it will become r, that is A0 into n is 4, so 16 divided by z is 1. So 16 A0, which is option C. Is there any other way to do this? Yes, you could have used this also. 1 by lambda is equals to r z square 1 by n1 square minus 1 by n2 square. From there also you could have calculated n2, this n final. Okay, from there also you could have calculated what is this, and that way also you could have done this. Both ways are there. I did this way because this thing is given, so I use this. Okay, everything got simplified from there. Now let us talk about the limitations of Bohr's theory. So there are certain limitations for this as well. First is, it is only applicable for single electron species, it is not applicable for multi-electron species. Why so? Because when you are writing this electrostatic force is equals to mv square by r, what if there is other electrons also in the outer orbits, and how you will take all that forces, electrons are moving also, it becomes a kind of very complicated. So considering that is like here in Bohr is not possible, isn't it? Therefore it is only, this model is only applicable for not applicable for multi-electron species. Next is, we got how to write the frequency of the emitted photon when an electron de-excites from one higher energy to lower energy, frequency or wavelength we can write. But if I ask you what will be their corresponding intensities if a hydrogen gas is there, okay, or the total, all the gases are excited, okay, by electromagnetic radiation, now they de-excites, which intensity will be more, which intensity will be less, and on which things it will depend upon. Are all intensities are going to be same? Certainly they are not going to be same, okay. So that thing is not explained. You can find the particular wavelength or particular frequency, but you cannot find the corresponding intensities, okay. So some are having very low frequency also, but why that is low and how to calculate that, that is not there. Now, de Broglie explanation of Bohr's second postulate. As I mentioned, de Broglie told that angular momentum in nth orbit has to be integral multiple of h by 2 pi, but he didn't mention why that is so. So de Broglie explained that, why that is so. Now the same thing comes here, that electron behaves like a wave, okay, and as electron is moving in fixed orbit, okay, a wave between, you can say, between two fixed, you can say, ends in a string, if a wave is there, then what will happen? There will be a standing wave, isn't it? If the thing is stable, so then there will be a standing wave, okay. So electron is in the stable state, so there has to be a standing wave. This electron will behave like a standing wave here, okay. Yes, so electron in nth orbit will behave like a standing wave. Now this standing wave, now standing wave have their limitations. You cannot have any frequency of a standing wave. No, if the string is there, the two rigid ends has to be nodes. That limitation is there. Okay. Now here the two ends are you can say connected like this. So this standing wave has to be integral multiple of this total length. If I talk about this total length, has to be integral multiple of the wavelength lambda. So either it can be lambda, 2 lambda, 3 lambda, 4 lambda, like this. So this, my total length of the string here, not exactly string, I am just telling, this total path length has to be this 2 pi Rn, Rn means the radius of the nth orbit, is basically equals to n times of lambda, and n is actually the principal quantum number here. Got it? Why? Because electron behaves like a standing wave. So here I can say that my I related my 2 pi r as n lambda. Now second postulate, we have MVR, that is equals to n into h by 2 pi. That relation is there. Okay. We have this relation. Now this lambda is the de Broglie wavelength. Of electron. So you can write this as h by mv. Two pi into Rn is equals to nh by mv. So mv into Rn you can take here. This is nh by 2 pi, and I got my angular momentum L of the nth orbit as nh by 2 pi. And which is the same thing, the second postulate. This was the second postulate, and we derived this second postulate by this analysis. Got it? Is that clear? So this is the proof. Now let us do some questions on this. An electron in ground state of hydrogen atom has orbital radius this meter, while that of electron in third excited state is this, the orbital radius are mentioned. The ratio of de Broglie wavelength of electron in the excited state to that in the ground state. Okay. So how I can relate? 2 pi r is basically equals to n lambda. This is how we can relate. Okay. So if I have to write for the first for the ground state, r is equals to let us take r is my this what is given, so I can write that as my r1. So r1 is equals to n into lambda 1, the corresponding de Broglie wavelength. Now what is that? Which excited state it is? Third excited state, means n is equals to 3. So 2 pi, here my r3, this is n into n is 3 there, okay. This is 3 into lambda 3. Here my n was equals to 1. So this was 1 into lambda 1. Now take the ratio. 2 pi got cancelled. Okay. So what I need? The ratio of de Broglie wavelength of electron in excited state to that of the ground state, means lambda 3 by lambda 1. Lambda 3 by lambda 1 comes out to be r3 by 3r1. Is this clear? Lambda 3 by lambda 1 is equals to r3 by 3r1. Now value of r3 is 8.48 into 10 to the power minus 10. Anyways, that is okay, 10 to the minus 10 is there. So 10 to the power minus 10, let me write, then I'll simplify. This is 5.3 into 10 to the power minus 10. So I can write this as 5.53 into 10 to the power minus 10, okay, angstrom into 3. So how much it will become? 8.48, and this is 8.48 divided by 0.53 divided by 3, and this comes out to be, oh, it's not coming properly. How much it is? Wait a minute, I did a mistake. Third excited state is there. Third excited state means n is equals to 4. The same, you know, these type of things happens. Anyways, universal. So here my n is equals to 4, not 3. This is n is equals to 4. This is also n is equals to 4. This is my r4 and this is my 4. Yeah. Now I can say, and let me write this as lambda 4. Yeah. Now I can say this my lambda 4 by lambda 1. This is equals to 1 by 4 into r4 by r. So what is r4? 8.48 into 10 to the power minus 10. Here 4 into what is r1? 0.53 into 10 to the power minus 10. Now this is 8.48 divided by 4 divided by 0.53, and this comes out to be exactly 4. Now I could have done this by relating r4 and r1 also, because r is proportional to n square by z. So this will be 4 square, and here this r1 1 square by z. Anyway, z will get cancelled. So 4 square by 4, that will come out to be 4 only. But I put it like this because it was mentioned in the question like that. So accordingly also we can put. But anyways, that is not required. You can just directly use r is proportional to n square by z. From there, calculations are not required then. Now atomic collision. Atomic collision is not much asked in mains. In advance there were questions, okay, 2025 also we had one question from atomic collision, good quality question. But here we'll discuss the relevant thing for mains, okay. So I will not go into much depth. So don't think like we are talking about, we are going to talk about the collisions in that much detail. No, that is not required for mains. So if you have to let us take excite an electron in a hydrogen atom. So what are the ways how you can supply energy? One thing is like you can photons are there. Okay, so photon comes, electron absorb photons, gets energy, go to the higher level. That is one simplest thing. Another thing can be, let us take some nucleus comes, hit the hydrogen atom, collision is, let us take inelastic, that released energy is somewhat, you know, use some fraction of that is used as for the excitation, another fraction goes as the kinetic energy. That also can happen. Okay, inelastic collision has to happen because some loss has to be there. If elastic collision is there, then excitation will not be possible. Okay, so collision has to be inelastic. It can be perfectly inelastic also, it can be inelastic also. So let us take some, this is my hydrogen atom. Okay, and some nucleus is coming, so some neutron is coming. Okay, neutron is coming. Okay, so this neutron comes, it hits, so it can be like, you know, this gets excited, let us take initially this was in ground state, electron, and then it went to the excited state. They are having some kinetic energy also. Okay, so basically here energy loss is utilized as in two parts. First is the kinetic energy of atom plus neutron. Okay, and plus the energy needed for excitation. Simple thing. Don't go into much detail, as I am saying, don't go into much detail, that is not required at all. Next thing is, let us take a hydrogen atom is there initially at rest, it emits a photon, electron de-excites from higher, it emits a photon, then what will happen? Certainly photon will go, it will have its own momentum in the opposite direction, the momentum will be there for the hydrogen atom. Okay, so let us take, this is my hydrogen atom, this is at rest, this is excited. Now the electron de-excites, photon will be emitted. Okay, so this is, let us take my photon. So this hydrogen atom, because conservation of momentum will be there, total initial momentum is 0, final momentum has to be 0, this hydrogen atom will have its momentum in this direction, or I can say velocity in this direction, because total momentum has to be conserved. Photon is having momentum towards the right, atom will have momentum towards the left. These basic things are required for this, no more details. Let us see some of the questions. So when a hydrogen atom going from n is equals to 2 to n is equals to 1 emits photon, its recoil speed is x by 5 meter per second, where x is use my mass of hydrogen atom in this. Okay, so my hydrogen atom is going electron in the hydrogen atom is going from n is equals to 2 to n is equals to 1. So the photon is little let us take going like this. So how much is the wavelength of the photon? Let us take that is lambda. So I can say my 1 by lambda is equals to Rydberg constant into z. Z is 1. Okay, so into 1 by n1 square minus 1 by n2 square, so 1 minus 1 by 2 square. So this is my 3r by 4. Okay, so I will say my momentum of H atom is basically equal to, in magnitude, okay, momentum of photon. This is what I'm talking about, the magnitude. Don't take in the direction sense. So how much will be the momentum of the photon? H by lambda. This is h by lambda, so that is 3rh by 4. Momentum of H atom, you can just write mass into velocity. So velocity you can write from here as, okay, so velocity you can write from here as 3rh by m, like this. M I took here 4m. Just as simple as that. And now let us do some calculations. So V comes out to be 3 into R is 1.097 into 10 to the power 7 into 6.6 into 10 to the power 34 minus 34 divided by 4 into m is 1.6 into 10 to the power minus 27. Now you can do the calculations and you can let me know what is the value of x in the comments. So put the timeline of the video, put your answer. I have seen students putting some of the answers as I asked, so you can also participate. Next question. A free electron of 2.6 electron volt energy collides with H plus ion, okay. This results in formation of hydrogen atom in the first excited state and photon is released. Find the frequency of the emitted photon. Just apply conservation of energy. Initial energy is 2.6. Okay, so I'm just writing, my total initial energy is equals to my total final energy. Now initially this free electron is having how much energy? 2.6 electron volt. Finally, this results in a formation of hydrogen atom in the first excited state and a photon is released like this. So finally it is in the first excited state. First excited state means how much energy? Minus 3.4 electron volt. First excited state means n is equals to 2. So energy in the nth orbit is minus 13.6 divided by 2 square. Okay, this is for the first excited state. So this will become, okay, 3.4 minus 3.4 electron volt. So for this electron, the energy, total energy is minus 3.4 electron volt plus the energy of the photon. So plus the energy of the photon. So energy of the photon comes out to be 2.6 plus 3.4. How much it is? 6 electron volt. And this from here what I need? The frequency, and this I can write as h into mu. From there I can find what is mu. So mu will be, what is h? H is 6 electron volt. So 6 into, convert electron volt to joules. Okay, so 1.6 into 10 to the power minus 19 divided by h, that is 6.6 into 10 to the power minus 34. So from here we can simplify it. Let us see. This is 6 into 1.6 divided by 6.6. So this is 1.45 into 10 to the power, how much it is? 15 hertz. We want our answer in megahertz. So this will be 1.45 into 10 to the power 9 megahertz. B option will be there. Is this clear? Easy to understand? Yes. Okay. Now let us talk about X-ray. How X-ray basically is produced, we are going to talk about here. Now X-ray we had talked about in electromagnetic spectrum also. Okay, when we discussed few of the things, fundamental things, which I already mentioned here. First thing is the range of the wavelength, that is this. There are how it is produced, I am going to talk about in detail, so I am not talking about this right now. Application of X-ray, you know, in medical imaging is there, okay. So we have, like, if a bone fracture or something is there, we need to see, okay, where the fracture is there, how the fracture is there, whether that is improved or not. So for that we use X-ray, okay. And then security scanning, we have crystal structure, we have certain types of treatment of cancer, we use X-ray. These are some applications. Let us talk about the production of X-ray, and this is using the collage tube experiment. Now here what is basically happening is the electrons, now one thing was there, that if photons falls, the electron can absorb the photon and electrons will be free. This is one thing. Now symmetricity exists in nature, opposite should also happen. If electron falls on the metal surface, okay, then some high energy photon should be emitted. Those are X-rays that we will discuss. Okay, so just the opposite of this photoelectric effect. Photoelectric effect, photons are falling, electrons are emitting. X-ray means electrons are falling, photons are emitting. Okay, so here first thing is we are having this filament here. Okay, so here current will come and all electrons will be emitted from this filament. This is a vacuum tube, okay. Electrons will be emitted. Now these electrons are accelerated through very high potential difference. Now if you see this potential difference, it is of order kilovolt, high potential difference. Now this high potential difference, due to this high potential difference, the electrons will gain lot of energy, and with very high energy they will strike this target metal. When they will strike this target metal, then the X-rays are emitted. How actually happens there on atomic level, that we will discuss in a while. Okay. Now certainly very high energy electrons are hitting the surface. The surface should have a high melting point such that it will not melt. Therefore we are having target metal of having very high melting point. Okay, so this is the structure. This is copper you can say block, and it is attached with a metal which is having very high melting point. Electrons are ejected from the filament. They are accelerated due to this potential difference. With very high energy they will strike, and eventually we will have these X-rays. We don't need any more details in this. Now there are two types of X-rays depending upon how they are produced. Okay, so first thing is the continuous X-rays. How these continuous X-rays are produced? Now this is that my high energy electron. High energy electron is coming, passes like this, deflects. Okay, so what will happen? It will slow down, and some part of that energy is emitted as X-ray. This photon is emitted here. Some part of that energy is emitted as X-ray. Now how much part is emitted? It depends how actually the electron is coming. So if the electron is coming, you know, exactly head on, maximum energy you can say will be lost, and then very high energy you can say X-rays will be there. Here some part of will be lost. Okay, this is of highest energy here. Here then medium energy is there. Here the lowest energy will be lost. If the maximum energy is lost for an electron, then the particular you can say wavelength that will be emitted will be least wavelength. High energy means the least wavelength, you know that. Least wavelength, that we call as the cutoff wavelength. Okay, you cannot have any wavelength greater than that. Okay, so this is my intensity versus wavelength curve. This is the minimum wavelength here. This is the minimum wavelength here. So we call that as my cutoff wavelength. So this is my cutoff wavelength. Okay, certainly that intensity will be minimum, because it's very difficult, you know, for that particular condition that the electron is just coming head on. That okay, so the electron goes like this with some lesser energy. That difference in the energy is emitted as photon. Okay, so this way of production we call that as the continuous X-ray. Now cutoff wavelength means the minimum wavelength of X-ray emitted. Okay, so I can say the total energy of the electron is lost. Let us say it comes and slows down like this. So total energy of the electron is lost. So my kinetic energy of the electron, how much that will be equal to potential difference into the charge. This will much will be the kinetic energy. Okay, V is the applied potential. This is equals to becomes the energy of the photon. So hc by lambda. So lambda comes out to be hc divided by E into V. hc lambda becomes hc divided by E into V. Here V is my potential difference through which electron is accelerated T is speed of light, E is charge of the electron, H is Planck's constant. Next way of production of X-ray can be this we call as the characteristic X-ray. So this can be like this. Electron is coming, it strikes one of the electron in the orbit, knocks it down. So this electron moves out and the electron which was coming also, it moved away. Now this is empty space. Now here it is an empty space and electron from the higher orbit will de-excite and occupy this empty space. Yes. During that de-excitation process some energy will be released. Yes, that will be released. So this will be released as a photon. This becomes my characteristic X-ray photon. Clear? Again repeating, electron comes with high energy, knocks out one of the electron, both the electrons goes out. Okay, not that the initially is there. Okay, both the electrons goes out. Okay, now there is empty space. Another electron from the higher orbit will occupy that space and this will become my characteristic X-ray. Now, depending upon electron from which state to which lower state it occupy, we name the X-ray. If it occupy from n is equals to, you can say, if it this level we say K, L, M, N. Okay, if it is occupy from L to K, this is my first K. Okay, so K alpha, then K beta, then K gamma. Similarly here for L alpha, okay, L beta, and then L gamma, like that. And these intensities will be just spike like this. In this we can say this particular wavelength, so then this particular wavelength. So these spikes denotes the characteristic X-rays. So from here to here it is going, so this is my K alpha, then here to here it is going, this is my K beta in K series, then in K series we are having K gamma. Okay, so here this is my L series, L alpha, okay, this we call about L alpha, then this is my L beta, L gamma, like that. And that particular, you can say, difference in the energy, that will be equal to the energy of our characteristic X-ray photon. That point is clear to us. Let us do this question. An electron having de Broglie wavelength A is incident on target in X-ray tube. Cutoff wavelength of emitted X-ray is. Okay. De Broglie wavelength, I think this should be lambda. So cutoff means the maximum. So Hc divided by lambda, this energy of photon will become equal to my initial energy, that is my energy of the electron. Okay, energy of electron. How to write the energy of electron? Half mv square we can write. De Broglie wavelength is given for the electron. This is my lambda photon. Okay. De Broglie wavelength of the electron is given. From there I can write the momentum. We know momentum P is equals to h by lambda, and my energy will become P square by 2m. So P square by 2m is basically equals to hc by lambda photon. P square means h by lambda, so h by lambda square by 2m is equals to hc by lambda photon. Okay, now from here one of the h will get cancelled and I need to write lambda photon cutoff wavelength. Okay, this is my cutoff wavelength. So from here my lambda photon becomes C 2m lambda C, 2m lambda into C divided by h square. 2m lambda into C divided by h square. Okay, no option is matching. I think there h by lambda, yeah, everything seems fine. Let us see, there must be a typing error in this question. Let me check again. So this is a typing error. What are the actual options? I'm just seeing that. Two m lambda square by h. Oh yeah, 2m lambda 2mc lambda square by h. Okay, I'm getting lambda square. Yeah, I think I did a mistake here also. This is lambda, so this will be lambda square, and h square will not be there. Yeah, I wrote it incorrectly. This will be 2m hc, no, not h, 2m lambda square c divided by h. It should be like this, and this is given in the second option, 2mc lambda square by h. Yes. Next thing, okay, now let us discuss about Moseley's law. So it relates the frequency emitted for the characteristic X-ray, okay, with the atomic number. So this root of frequency is basically proportional to, you can say, z minus b, and here proportionality constant becomes our a. A and b are constant, b we call as the screening constant. Now for you can say k alpha, this b is equal to 1, you can remember it. K alpha line, b is equals to 1. And if we draw this plot between the frequency of the radiation that is emitted with z minus b, certainly this is a straight line. Z is the atomic number of the target metal. Now let us do this simple question. If lambda cu is the wavelength of k alpha X-ray line of copper, and lambda mo is the wavelength of k alpha for the molybdenum, yeah, k alpha X-ray for the molybdenum, atomic number 42, then the ratio of lambda cu by lambda mo is, first of all, we know root of frequency is proportional to z minus, he is talking about k alpha, we know there b is 1, so z minus 1. So my frequency is proportional to z minus 1 square. Therefore my wavelength is inversely proportional to z minus 1 square. Therefore if I write z lambda cu by lambda mo, this will be equal to this z minus 1 for cu, what is that? 28 square, and here we will have 41 square. So 41 by 28 whole square. Let us do 41 divided by 28, and let's do square. So this becomes 2.14, that is option B. Okay, not, I think questions are not much asked from this X-ray portion, okay, but still you can revise it quickly, it's not that much complicated. Now we are moving to next chapter, that is nucleus. So let us discuss about composition of nucleus. So from Rutherford model we got that yes, the entire positive charge is there in the nucleus. So basically nucleus is made up of protons and neutrons. It has protons and it has neutrons. Protons has positive charge, neutrons are neutral. Now you may say, sir, how is it possible? Positive charge and neutral charge, and they are placed in a very compact space. Yes, the space is very compact. So how is this possible that they are not repelling each other. There must be Coulombic repulsion, isn't it, between them? Yes, there has to be. So let us say this is my nucleus. Okay, so here we are having protons also and neutrons also. Okay, some of them I will mark as positively charged, almost half, may not be exactly half, like this. They are placed in a very compact space. There has to be repulsion. Positive charge placed so close to each other, they will repel like anything. But now here we are having another additional force, that is nuclear force. Okay, actually that force is binding it, and that nuclear force is actually strongest. Okay, nuclear force is strongest. Nuclear force is there, and which is binding us. So nuclear force is actually strongest. So first we have the nuclear force, then comes the electrostatic force. But the problem with the nuclear force is it is very short ranged. If the distance is very small, of the order of Fermi meter, it will be high. If the distance is a bit greater, you know, at all of a sudden you can say this nuclear force will decrease, and then the Coulombic force will be there, then there too much repulsion will be there. Okay, this is very short ranged. The distance has to be of order of Fermi meter, 10 to the power minus 15. Okay, this nuclear force is binding is. Now nuclear force is independent of charge, independent of the polarity. Okay, don't think like positive will have a repulsive nuclear force and positive neutral will have attractive nuclear force. No, it is charge independent. It is independent of charge, even by polarity or something. Okay, charge or polarity, anything you can say. So due to very strong nuclear force, this nucleus is bound. These all the protons, all the neutrons are bound in a very compact space. So this is the composition of nucleus. Okay, so in nucleus we are having protons and we are having neutrons. So we define a term that we call as the mass number, and the mass number we denote with A. So this mass number is equal to the total number of protons plus the neutrons. Okay, so here we are having number of protons, NP, or I can say I'll write it in Y, plus the number of neutrons. Okay, just a minute. So we are having the number of we are having protons and the neutrons that are there inside the nucleus. So when we say mass number, this is the count of protons plus the count of neutrons, and sometimes we'll talk about that in later. Okay, so number of protons is basically what? The number of protons that are there in the atom. How many protons will be there? That is equal to the number of electrons, because atom is a neutral particle, isn't it? So and that is my equal to my atomic number. So number of protons is basically my atomic number, Z, and number of neutrons you can write as number of neutrons, Nn. Okay, and this becomes my mass number. is the mass of my you can say nucleus is equal to the sum of all the neutrons and the sum of all the protons, mass of all the protons. Is it like that? Not actually. There is some mass defect there. Okay, so actually if you want to find the mass of this nucleus, don't just there are 4 protons and there are, let us take 4 my neutrons there, so it will be 4 mass 4 into mass of proton plus neutron. No, not like that. There will be mass defect also. We will talk that about that. Yes, so any atom is there. So here we denote with Z, here we denote with A, the mass number. Okay, so if you are asked how many number of neutrons are there, I will say my number of neutrons will be equals to A minus Z. Sometimes this whole count is mentioned as number of nucleons. Number of protons plus number of neutrons we call as number of nucleons. Okay, so sometimes we call this as number of nucleons also, same thing. So this is my nucleons. Now size of nuclei. So the size of nuclei is related with the mass number. The radius of the nuclei is related with the mass number as R naught into mass number to the power 1 by 3, where this R naught is the constant whose value is almost 1.2 into 10 to the power minus 15 Fermi meter. Sorry, minus 15 is there, so meter. So Fermi means 10 to the power minus 15. Now, if we try to find the density, let us find the density of neutron. Many times the questions are asked from this. Density of, sorry, not neutrons, nucleus. So density of nucleus, we will say the density is equals to mass divided by volume. This is how we say. Okay, so mass, how to write the mass? Mass will be proportional to the mass number. Yes. Okay, so mass will be proportional to mass number. I'm just writing the proportionality. Mass number, that is A, divided by volume is 4 by 3 pi r cube. So this is my r cube. 4 by 3 pi is constant, so I'm just writing the proportionality relation. From here I can say density is proportional to A divided, what is R? R is R naught into A to the power 1 by 3. So R naught cube into A to the power 1 by 3 cube is A. So basically this density comes out to be independent of the mass number. Density is independent of nucleus is independent of mass number. This is very important thing. Many times in mains we have seen question, find the density of this nucleus and this nucleus, atomic number is this, atomic, that is 1, and sometimes they directly say what is the relation of the density with the mass number or like that. Okay, so keep this thing in mind, that is independent of the mass number. I'm highlighting it. Okay, let us discuss this question. Ratio of density of oxygen nucleus. Okay, this is binomial. What is this? And helium nucleus. Oxygen nucleus and helium nucleus. What is the density ratio? 1, always independent of the mass number. So it doesn't matter what is the, you can say, atomic number of the atom, density is the same of the nucleus. Yes, it's like, from one liquid only you are making all the nucleus. Okay, an atom X, this question was asked in 2026 January attempt this year. Okay, an atom X is bombarded by a shower of fundamental particles, and the answer was incorrect by NTA, that is also there. And fundamental particles in 10 seconds, the atom absorbed 10 electrons, 10 protons, 9 neutrons. The percentage growth in surface area of the nucleons recorded will be. Now radius is R naught into A to the power 1 by 3. area, that is 4 pi r square. Okay, let me write area instead of A because A is also mass number. Surface area is equal to 4 pi r square when we do. Okay, so that will be proportional to A to the power 2 by 3. This is the relation between the area and the mass number. So initially my mass number was 8. Okay, so if I say area, initially this is 8 to the power 2 by 3. So 8 to the power 2 by 3, that is 4, proportional to 4. Finally my area will be proportional to, what is the 8 was the mass number, it absorbed 10 protons and 9 neutrons. So the mass number will increase by 10 plus 9, 19 to the power 2 by 3. How much it is? This is 18 plus 9, 27 to the power 2 by 3, that is 27 is 3 to the power 3. So this will become 3 square, that is 9. So initial area and final area are coming out to be 4 by 9. What we need, the percentage growth in the area recorded is. Okay, so A initial divided by A final comes out to be 4 by 9. Now I need percentage growth. So A final divided by A initial minus A final will become 9 divided by percentage growth. Final is greater. So final minus initial I will write here. A final minus A initial. Okay, so this will become 9 minus 4. 9 divided by, everything seems fine. 9 minus 4, yes, it seems fine. Sorry, percentage growth now. How much increased? Everything was not fine. How much increased? Increase will be A final minus initial. This is the increase. How much was the initial? This is A initial. This is how we write, yeah. So A final is 9 minus 4. Here this A final minus A initial, 9 minus 4 divided by A initial was 4. So this becomes 5 by 4. So percentage will be into 100. So 5 by 4 into 100, this is 125. So 125% growth is there in the area. Option C. In the end, the options were wrong. Actual question. So this was a bonus question. Now, nuclear binding energy. As I was saying that if I ask you how much is the mass of the nucleus, you will say, sir, there are protons, there are my neutrons. So just sum up the total masses of the individual protons and neutrons, that will be equal to the mass of the atom. But actually that is not there. The mass of the, not atom, nucleus, mass of the nucleus is a bit less than that. Okay, so let us take, this is my not atom, nucleus, sorry, again I mentioned atom. So mass of the nucleus is a bit less than that. Now this is my nucleus. Okay, let us take it as having Z as my number of protons and N as the number of neutrons. So individual mass, if I talk about, mass of the composition, that is Z into mass of proton, Z times into mass of proton plus N times mass of the neutron. Now mass of the proton, this N, the mass of the, number of the neutrons you can write as what? My atomic, my mass number minus Z. Okay, Z number of protons are there, total mass number is A, so A minus Z is number of protons, number of neutrons into mass of the neutrons. This becomes my mass of the composition, but the mass of the neutron will actually be less than that. Let us take M as mass of the nucleus, mass of the nucleus is actually less than that. Okay, so this mass of the nucleus is less than this mass of the composition. and the difference between the two is the mass defect. Okay, so mass defect, that is my delta m, that will be equals to m minus this total z into mass of proton plus a minus z into mass of neutron. This becomes my mass defect. Okay, now this mass defect comes, that mass defect, where it goes, it is released as energy, and that energy we call as the nuclear binding energy. Okay, now when these compositions comes together, nucleus is formed, and that mass is released as energy. And if you have to break down the nucleus into the individual composition, means the individual protons and neutrons, then you need to supply the same amount of energy. Okay, you need to supply the same amount of energy. So there, that is also binding energy. Binding energy can be defined in two ways: either the amount of energy that is released when the individuals forms the nucleus, or the amount of energy that is needed to be given to break down this into the individual neutrons and protons. Okay, so my binding energy is equal to delta m into c square. This becomes my binding energy, and I can write this, if you take this delta m in terms of atomic mass unit, in terms of U, okay, this delta m in terms of U, so you can write this as delta m in U, okay, atomic mass unit, into 931.5 mega electron volt. This much energy will be released. You can, write this corresponding formula directly, because many times the question, in the question they want us to report the answer in mega electron volt. So there, if you do delta m that is given in U, then you convert to kg, then you multiply this with 3 into 10 to the power 8 square. It will be a very long way to, and then eventually converting that to mega electron volt. So just take delta m in U, multiply that with 931.5 to get the direct answer in mega electron volt. Now binding energy per nucleon. Binding energy per nucleon means divide this with number of nucleons, divide with the mass number. So binding energy per nucleon is equals to my total binding energy divided by the number of nucleons, that is my mass number. And it shows us the stability. Greater the binding energy per nucleon, more stable the nucleus will be, because to break down that nucleus you need to supply high energy. So greater the binding energy per nucleon, more stable it is. If you see this graph of stability, this graph of average binding energy per nucleon and mass number, so here the binding energy is less. Here the binding energy per nucleon is less, and here also the binding energy per nucleon is less. Here the stability is more. In this region stability is more. In these two regions stability is less. In this region also and in this region also. So what will happen, to become more stable, these nuclei will show fission, okay, not fission, fusion, okay, fusion, so that eventually the you can say the mass number is increased, they will go in this region, and these will show fission to go in this region for greater stability. Okay, so they will show fusion and they will show fission to become more stable. Let us do some questions on this. The mass of proton, neutron and helium nucleus are this, this and this. The binding energy of helium nucleus is, so basically I'll say my binding energy is delta m into c square. This is how we write, or write this delta m in atomic mass unit and multiply this with 931.5. This answer will be in mega electron volt. Now first of all I need delta m, everything is given in U, so let us do with the second method. Okay, so what is delta m? Delta m is, oh wait a minute, I did one thing. when I was writing this mass defect, this thing is more. So when I'm subtracting, I should subtract from this thing, okay? This, it will be minus of m. It should come here, other side, because the first quantity is more. Here we were. Okay. So mass of the individuals in helium nucleus, we are having 2 protons and 2 neutrons. So the individual mass will be 2 into mass of proton plus mass of neutron. This becomes the mass of the composition minus the mass of the helium atom you do. So what it will be? 2 into 1.0073 plus 1.0087, okay, minus mass of helium 4.0015. This is in U. Let us take help of calculator to do it quickly. 1.0073 plus 1.0087, okay, into 2 minus 4.0015, and this comes out to be 0.0305 U. This becomes my delta M. So my binding energy is delta M into 931.5. So into 931.5, this becomes 28.41. okay. So when I write binding energy here, this will become my delta M into 931.5 mega electron volt. So this is 0.0305 into 931.5. So this comes out to be 28.4107 mega electron volt. 28.4, B option. Simple thing. Okay. Next is binding energy of a certain nucleus is this. How much the difference between total mass of all nucleons and nuclear mass of the nucleus. Binding energy is delta M into C square. Basically he is asking what is delta M. So delta M is equals to binding energy divided by C square. Now how much is the binding energy? That is 18 into 10 to the power 8. So 18 into 10 to the power 8 divided by C square. 3 into 10 to the power 8 square is 9 into 10 to the power 16. Yeah. So this is 2 into 10 to the power minus 8 kg. If I convert this to gram, so this will be 2 into 10 to the power minus 5 grams, and this will be 20 micrograms. Yes, 20 micrograms. Q value. In a nuclear reaction, certainly we know that mass is not conserved. In other reaction, mass is conserved, but in nuclear reactions, the mass is not conserved. So you can say you'll have some of your reactants, some of your product, okay. So there will be mass defect when the energy is released or energy is absorbed, anything. So delta M, that is my mass defect, this is equals to my mass of the reactants minus mass of products. Okay. Now if you know delta M, you can write Q is equals to delta M into C square. Simple thing. And again I am saying you can write it like this, delta M in U into 931.5 mega electron volt. The same thing. Same thing you are getting here. Okay, let us do quickly a question. So A is getting to B, D, and some energy is released. Mass of A, mass of B, mass of D is given. We need to find the energy released S. So first find the defect mass. Okay. So first find the mass defect here. Mass defect will be mass of A minus mass of B plus D. Okay, how much it is? Let us do it quickly. I'll take help of my calculator. Mass of B and D, this is 234.04363. This is the mass of B, yeah, and mass of D is 4.00260. This is the total mass of A and B. Subtract this quantity from mass of A. Mass of A was 238.05079. So this is 0.0045, 0.00456 U. Multiply that with 931.5. This becomes 4.247. Yeah. Okay. So multiply this with, so my Q is equals to 931.5 into 0.00456, and this comes out to be 4.2476, which is 4.25. Next question. In a reactor, 2 kg of uranium fuel is fully used up in 30 days. The energy released per fission is this. Given that Avogadro number is this per kilomole and 1 electron volt is this, the power output of the reactor will be. Power output means per second how much is the energy released. So in 30 days 2 kg of uranium is used. So 2 kg of uranium, how many moles? 2000 gram divided by molar mass 235 gram. This many number of moles. How many number of particles? Multiply that with Avogadro number 6.022 into 10 to the power 23. This is the number of the total number of atoms we got, and per atom we are having energy of 200 mega electron volt. So 200 into 10 to the power 6 mega, convert electron volt to joule, so 1.6 into 10 to the power minus 19. This is my total energy, and this energy is released in 30 days. So per day if I talk about, divide this with 30. Per hour if I talk about, divide with 24. Per minute if I talk about, divide with 60. Per second, divide with 60 again. So this is the energy per second. Okay, so this becomes my power. Now I ask you to do this calculation and put your answer in the comments. So do this calculation and put your answer in the comments. So first let me revise again. First, finding the number of moles, total number of particles, total energy per second. So this is all from my side in this discussion. So we have covered all the details of modern physics, and modern physics is really a very high weightage you can say topic in mains. So make sure you don't miss any part of this video. If you are having any doubts, anything you want to ask, please mention in the comments. Okay, I'll be there in the comments to reply. And if you understood everything, or if you like few things, so make sure you give the appreciation in the comments, because it brings a lot of positivity to us. And after this, make sure you have some practice also yourself. So we have practice sheets for you and this class notes for you in the link that is given in the description. So you'll get all the things from there. So thank you all. Have a nice day.